Okay. Good morning, everyone. So while you're settling down, so welcome to day 3 of this GIAN course on AI and medical image informatics for cross-scale disease characterization and precision medicine. So I know it's a Sunday. You'd rather be in your wherever you are and spend the day in bed probably, but yeah, we're here. So we'll try to make the best use of it. So I really had a good time yesterday after teaching. I think I got time to explore a little bit of Rourkela, went to Hanuman Vatika. It's a good place. Rourkela is a good place. You have to, you learn to fall to love with it. So yeah. Anyways, so let's get started. So today's theme or today's topic will be, so we'll be covering a little bit of going into some of the in-depth topics in digital pathology, a little bit more advanced topics. So yesterday we saw how digital pathology is reshaping the domain of pathology. Not just helping clinicians, but also helping researchers alike, and how it is facilitating collaborations between clinicians and researchers. And it's also so we are at that juncture where we can use multimodal data, which includes not just radiology and let's say genomics, but also pathology data to build these multimodal predictors of or biomarkers of disease diagnosis, prognosis, and treatment response assessment. Okay, so one of the challenges, if you remember the last slide where I covered a little bit about the challenges of digital pathology yesterday. So one of the standing challenges is interpretability and transparency. So when you hear or when you look at these two words, interpretability and transparency, what comes to mind? So what do you think this means, interpretability? Anyone?
Interpretability means like once the decision is made, like you have to you have to make it in a structural format that like why and like how the thing is interpretability. When it comes to the transparency, like probably how good it made the decision, like whether it is factually correct or not, kind of.
Right. So yeah, so that's a good answer. What interpretability and transparency means. Now, why is this important, especially in this field? So we are talking about medicine, we are talking about medical imaging. So why do you think having interpretable or transparent models is important in this field? Anyone? Yeah. So can you just pass the mic?
Sir, explanation is required to trust the clinicians, whatever the AI models has generated the result.
Right.
So to trust in that report, the clinicians should go through that transparency, how it has made the decision.
Right.
So explainable in that sense.
Thanks. So you mentioned trust, right? So we develop AI models in our lab. Many of us do. There are multiple groups that do, but you'll see that ultimately not many of these or very few of these AI models see the light of the day. Not I would say hardly even less than 5% of these models ultimately make their way into clinic. So there are multiple reasons, and one of the reasons is that a lot of these models that are out there, even though their performance is good for whatever tasks they are they are trained to do, the models are not inherently interpretable, they're not inherently transparent. So what does that mean? So eventually the reason why we are building these models is we want the end users, who will be the clinicians, we want the clinicians to use these models. Now if the clinicians don't understand, and I'm not saying that understanding the math behind the model, but they should understand, let's say, what the model was trained on, what kind of data the model, what kind of data went into the training of the model, right? And also when the model makes its decision, what is the decision, like how does it make its decision, right? So it has to be transparent. Also, if there will be cases, not all models are 100% accurate. In fact, very few models are 100% accurate. Or you can talk about other metrics like AUC or F1 score, sensitivity, specificity, whatever metric you consider. None of the models are 100% correct all the time. So when models make their way into the clinic, and we'll cover this in a little bit more detail tomorrow in tomorrow's lectures, but before models make their way into the clinic, there are rigorous studies that are done to evaluate where the models fail. What are the false positives? Where are the false negatives? Why are they happening? So you'll see that when you publish papers, or when you read papers rather, you'll see that this analysis is probably not done in most papers. I mean, you'll just see a big table where where authors report the different metrics without really talking about or talking a lot about where the model fails. But that is something that is very important when it comes to translating these techniques or translating these models to the clinic, right? I mean, yes, by all means, you can publish your machine learning conference papers, your vision conference papers, but eventually, if you want the clinicians to learn about this technique that you have developed, or to adopt this technique that you have developed, you would at some point, you would want to gain their trust. And the only way you can gain their trust is by doing your due diligence when it comes to evaluating where the model fails, what are the failure cases, right? And when it comes to these models failing, what can you do to make these models better on such cases where the model has previously failed on? Okay, so all of these things become very important, and a lot of times, and I can say that we are also at times guilty of that, we don't really think about these things when developing a technique. We are all about, okay, we want to publish the next paper, right? We want to attend a conference, we want to have fun, right? So, but eventually we have to understand that these models, if and when they make their way into the clinic, they will impact the way clinical decisions are made, and at times lives might be at stake. So interpretability and explainability in clinical AI is very important. The first reason and the most important reason is that it can lead to improvement in trust and adoption of the model. So we'll talk a little bit, or we'll talk in detail about this tomorrow, but when it comes to model adoption, hospital systems, so there are many, so let's say that there's some tumor detection model or detection of pulmonary embolism, there will be multiple vendors, or there are multiple companies that can do that. How do the hospitals decide which company to buy their software from, right? So much of this can be dictated by how much transparent, how much interpretable these models are, right? So let's say that there are three of you sitting here, each of you has a model, and you have similar cost structures that you have. Let's say if a hospital wants, the Apollo hospital here wants to buy the model from one of the companies, one of the three companies here, they'll obviously have many financial decisions that they consider, but eventually there will be clinicians who will play a role in deciding which software or which model to deploy in the clinic, and one of the very key important factors will be model explainability and interpretability. Compliance and regulatory requirements. So a lot of times, when it comes to getting these tests, let's say you have some AI-based tests reimbursed by insurance companies, there are many regulatory requirements, and the model being interpretable or explainable can have a say there. Error diagnosis, like I said, we have to make sure that the models that we build, we look at where the models are going wrong, what sort of cases they are misdetecting, misdiagnosing, and we have to try to understand that to the best extent possible. Eventually, we want to get into personalized patient care, and that's why a lot of this becomes important. So we have briefly touched upon handcrafted features, deep learning features, but formally, how do you define, or how do you explain what deep learning is? I know that many of you here work with deep learning or have developed deep learning techniques, but what is deep learning and how is it different from traditional machine learning? Anyone? Yeah, so can you please pass the mic?
Yeah, so actually in deep learning what we do is we will have several layers built along with us, basically the big neural network that we build. And what internally deep learning does is it creates the representation schema of the data set that it goes through. And then during inference, once it sees the data set, it gives the right basically outcome.
Okay, so that's a little bit of a technical answer. So you had terms like representation and layers and neural networks. Can someone explain it in a simpler fashion? So what's deep learning and how does it differ from traditional machine learning? Somajit, maybe you can answer.
No, actually, one thing actually we can do, like when you have very large
simple
data
answer,
set,
okay?
or like when you're having very large data set or very complex data set, and where machine learning models are not doing well, then we can apply some deep learning techniques. Or like this is a very basic thing.
But that doesn't answer the question. So how is machine learning different from deep learning? Not the application side. So let's say you have a simple data set, coming back to our favorite cats versus dogs. Okay, so how would you design a machine learning system, or what would you do in order to develop or train a machine learning model, a traditional machine learning model, and how does that approach change when it comes to, let's say, training a deep learning model? Yeah, I'll come back to you with another question, okay?
Probably, I feel like maybe the dimensionality change. Maybe in traditional machine learning, like probably we'll use like normal one-dimensional data, and then like when it comes to the deep learning, like we can use like
you can still have one-dimensional data in deep learning.
Still, we can use it, but like most of the things that we do with deep learning is like related to the video and images. But when it comes to the machine learning, like we traditionally have gone. Probably we can say that like machine learning models have more explainability compared to deep learning when it in terms of that like interpretability and explainability, because like most of the machine learning models have the mathematical intuition. When it comes to the deep learning model, they lack that mathematical intuitions that a normal human beings, like general people can't understand what is happening. So probably that is why it is called internal layers are completely black box. When it comes to the machine learning, it is a little different than the deep learning. Like, so what happens is like all these machine learning techniques are high level mathematical models where you can actually see what is happening through the mathematical functions. Okay. But when it comes to the deep learning, it's not like that. It's a little bit complicated to understand.
Okay, so we are getting there. We are not there yet. So
I'll give it a try. So in deep learning, in machine learning, typically you would take your data set, extract some features, and then feed it into the model. Whereas in deep learning, you rely on the layers itself to do feature extraction.
Yeah. So that's why he's there and you guys are there. So simply put, when it comes to traditional machine learning, you have some feature extractor, so you know what these features are, right? So when it comes to cats versus dogs, for example, you handcraft what these features are. So simple features that can be used to differentiate a cat from a dog is, I don't know, like the shape of the head, right? Or let's say whiskers, presence of whiskers, the size of the body. So you know what each of these features are, and then you tell your machine, or you tell your let's not tell machine, let's not qualify it as a machine. So let's say it's some sort of a logic-based method. So you say that if the shape of this particular entity, if the shape is like this, then it belongs to class A. If the shape is of some other kind, it belongs to class B. Right? So it's a simple, let's say, a rule-based criteria that you have. So you know what the features are. Okay, so actually the answer was on the screen. So you know what the features are. And then you have you can have simple regression kinds of models, or you can have a little bit more complex random forest kind of models, or support vector machines. So all of these are examples of classifiers. So you extract your features, and then you provide these features as feature vectors to your classification model. And you brought this term of dimension. Right? So typically when it comes to traditional machine learning, the dimensionality is less, because there is only so many features that we can extract. Like we maybe 100 features, 1,000 features. So it's almost impractical to extract more than that, or more than a specified number of features. Then these features won't really have a meaning. But when it comes to deep learning, you have your cats data set and you have your dogs data set. You design your neural network. You provide your data set to the model, and you ask the model to figure out what these representations are, right? So what are the best, let's say, feature vectors that can separate out, that can differentiate a dog from a cat. Now when you look at finally what that model has learned, it will be a feature vector, but you don't really know what that means, right? So you lose interpretability. So let's say that you have, the final feature vector that comes out from here. So you have these different layers, the layers of neurons here, and then you have a feature vector that comes out from this let's say this black box, like you said, and it's a 1 cross f or 1 cross n feature vector. We don't really know what each of these features are, right? So these are just numbers. So that's fundamentally the difference between machine learning and deep learning. So machine learning, we know what the features are, and it's usually the dimensionality is less. Deep learning, you design your neural networks. It can be either a shallow neural network, or a deep neural network, or a wide neural networks. But eventually, you stack up different neurons. The neurons learn what the representation of the data is, and then you provide this representation to a simple classifier at the end to give you a decision. Okay. Now, foundation models. So we very briefly touched upon this, foundation models. But foundation models are nothing but deep neural networks. Okay. So I know Moinak asked this question yesterday, and I didn't really see a raise of hands. Maybe it was because of this. At this point, I'm too afraid to ask what a foundation model is, because everyone is using foundation models, right? So I mean, there are different kinds of definitions. Foundation model is a large AI model. It's a machine learning or a deep learning model that's trained on huge data sets, humongous data sets, can be applied across different use cases. Now, it doesn't matter what definition, where you take this definition from, the common theme that you see here is that broad set, massive sets of data. However, what's slightly different is that usually, for the most part, foundation models are trained on unlabeled data, right? So we do not, okay, so what does that mean? So when it comes to training a traditional machine learning model, you know what the labels are. So you know that this data set is a data set of cats, this data set is a data set of dogs, and then you train a machine learning model to distinguish between cats and dogs. Now when it comes to training a foundation model, you don't have labels, and so you don't really know it's a cat or it's a dog. You just have the entire thing put together, jumbled up together. You have this data set. You ask the machine to figure out representations of that data. You provide that, so that it's done through something called pretext tasks. Okay, and I'll tell you how that works. I don't have a slide for that, but let me try to explain. So let's say you have, you have an image here, and this image can be divided into n number of parts. I'm dividing the image into 4 parts, 1, 2, 3, 4. And this can be all the images in your data set. You can divide them into 4 parts using some sort of, let's say, logic. Now, what you do is, you take these 4 parts and you mix them up. So you have part 1 here, maybe you have part 3 here, you have 2 here, and you have 4 here. Now you ask your model, you train your model to take this mix up, like you basically have jumbled up your patches. You train your model to take this mix up patch bag and put it back. So basically you ask it to solve a puzzle, right? So that's one way of doing it. Another way of doing it is you have this image, you remove certain parts of the image, and you train a model to go back and fill in that blank, right? So imagine how is ChatGPT trained? So ChatGPT has been trained on a lot of the initial version. Let's say when it was unimodal, it was trained on a lot of text data. And how would you train a model? I know that some of you here work with NLP. So you have large sentences. For example, let's say you take this sentence here, and you sort of remove certain parts of that sentence. So let's say you remove this part, and then you remove this part, okay, and then you remove this part. So now you have hundreds of thousands of sentences. You remove parts of the sentence, and obviously this is a training data, so you know what the full sentence is, the complete sentence is. Now you train a model to go and fill in these blanks. So it will say a foundation model, also blank large AI model. It will tell you also known as large AI model, or there will be another probability where it will tell you a foundation model also maybe called as large AI model, and it will give you the probability of each of the words. So it's not just one answer, right? There can be multiple answers that can be filled into the blank, but there will be a probability to each of these answers. Now the word that has the highest probability gets filled into that, and it's not necessary that it will be correct. It can be wrong, obviously, but because these models have been trained on massive data sets, we see that the way these models work, it's almost perfect. Okay. So here are some examples of foundation models that you might have already used. GPT, Gemini. So most of you would have dealt with these models. CLIP is something we've used a lot when it comes to multimodal models, image and text-based models. SAM is the segment anything model, where you can I think Moinak touched upon this a little bit yesterday, where you can have some prompts, whether it's a bounding box or it's a dot. So you put that on that area, and then it will automatically segment it for you. DALI was used for image generation, BERT, which is a transformer. So yeah, so you have all these models. Most of these models actually have a transformer-based backbones, and all of these are foundation models because they have been trained on large amounts of data. So now you would ask me that I told you they were trained on unlabeled data. So then how can it go back, like how can this model be used to classify cats from dogs? So you use this model to generate representations of the data. So now the model actually knows what an animal looks like. It doesn't know what a cat looks like or what a dog looks like. It can give you a representation of an animal. Now you use that model as a feature extractor. You extract the representations of the animals that you have, and then you have a small supervised classifier at the end, right? So you can actually train a model based on the representations from the foundation model that, okay, this is a cat and this is a dog. So that's what you do. So the painting on the right, by the way, any artists here, anyone who's into art, into paintings? So this is actually by a very famous artist, Salvador Dali. So this painting is called The Persistence of Memory, and you look at this painting and you'll see that there's a lot of interpretations that you can have about this painting, and a lot of these interpretations can be, let's say, psychological, philosophical, mostly surrealist. Because you see, there's a clock there. Part of the clock you see it looks like a clock. The other part is warped, and then you have the tree there, which looks weird. So, as painters, as artists, we are all painters and artists are crazy people. So are we. But if you look at how to interpret this painting, you can have so many different kinds of interpretation. So I like to bring this up because there's some sort of an analogy between abstract paintings like this and foundation models. So this painting, even though it has one underlying scene, you can have many different kinds of interpretations, right? So similarly, foundation models also usually have a single pre-trained backbone. Each foundation model will have some backbone. However, you can use the foundation models for multiple downstream tasks, and the way you interpret it would depend on techniques like prompting, fine-tuning, conditioning. and so on. So one model, many meanings. Similarly, this, have one painting and you can have many readings of that painting. All these foundation models that are there, they're purely data driven. At least the initial foundation models that were published. So typically, none of these foundation models had anything to do with the domain. They would take information, they would take images from everywhere. Right? So ChatGPT was trained on text data, sentences data from everywhere. It didn't really matter whether it came from medical literature or non-medical literature. Right? So everything was put together into that one bucket. So it was purely data driven. And I did show you this slide on the first day. The goal, at least for us who work with medical data, should be to go from these purely data driven models to models that are data informed and domain inspired. And in this case, the domain is medicine. So today I'll talk about, or in the first part of the lecture, I'll talk about enhancing interpretability in digital pathology. First, interpretable feature discovery. So yesterday we saw how we can extract different kinds of pathomics features from our pathology images at a tile level. So this gives you a summary of the different kinds of features that can be extracted. So you have that digitized slide that we spoke about yesterday, and you can extract different levels of information. So the first level of information is some grayscale information. You can convert it into grayscale, and then you can extract texture features like heraldic features or Gabor features or different kinds of texture features. And then, if you remember, we had a small discussion on how we can compute graphs. So we can use models to identify where the centroids or where the nuclei are, and then we identify where the centroids of the nuclei are, and we construct graphs. Right? So using these graphs can let us do different kinds of analysis like proximity analysis. So how one kind of nuclei is located, how close it is to another kind of nuclei, what is the spatial proximity, how are they arranged with respect to each other, right? So you can do this kind of analysis. Also, other kinds of analysis like shape-based analysis, texture-based analysis, and so on and so forth. So these are the traditional pathomics features, which are obviously by design a little bit more interpretable than deep learning features, because in deep learning features, we don't really know what the features mean. So coming to a few use cases. So one of the use cases here that we worked on was predicting overall survival in early stage lung cancer. So these were images. These are actually tissue microarrays. We take these images, we use nuclear detection models, nuclear segmentation models. We identify where the nuclei are, and then we use an algorithm called a mean shift clustering algorithm. So what this mean shift clustering algorithm does is it clusters nuclei together based on certain features like their appearance or texture, and then it forms these local clusters of nuclei, and after that we design certain handcrafted features. And I'll give you an example of what we do here. So on the right of the screen you see this cluster, which is this green cluster here, and you have another cluster which is this red cluster. So you have this group of nuclei which has been clustered into this green cluster, and another group of nuclei which has been clustered into this red cluster. You construct a convex hull around each of these clusters, which is essentially just the boundary. In lay terms, it's the boundary that surrounds those two clusters. And then you look at the intersection, right? So, and there are so many different features that we can extract from this intersecting region. So any thoughts on what features we can extract from this intersecting region? So think of it as a Venn diagram, right? So you have something here, they're intersecting. What kind of features can we extract here? Do we have another mic in the room, by the way?
For example, if the first cluster is based on the similar shapes and the second cluster is based on the similar texture, then from their region where they are intersecting, we can infer that this region, they have both similar structure and they have both similar size. So we can infer the common features in the cluster.
Okay, yeah, that's something we can do, but I'm talking more about from a geometric perspective. So you have, let's say you have this convex hull here, you have this convex hull here. this is the intersecting cluster. This is the intersecting region, which looks like, based on my diagram. Actually, I should be drawing it here. Sorry. Based on my diagram, it looks something like this. So let's say this is the intersection. So what features can you extract from here? What geometry features can
we
you
extract the size of it, like how big the overlap is?
Right. How big the overlap? We can extract the perimeter.
Yeah.
Right. So we can maybe like fit a ellipse and extract some major axis, minor axis. So these are the different kinds of geometry features that we can extract. So what this would tell you is these clusters. When you look at these clusters, how close these clusters are, how far away these clusters are, right? And these features can be used as features for your machine learning model. So remember yesterday when Moinak said, like we covered the pi radiomics features, he also said that it's not necessary that we have to use the existing feature extraction tools. You can design your own features, and a lot of times these features come from intuition. So here we thought that, okay, since we wanted to quantify the interaction between the different clusters, let's start with very simple features. And this was clearly an example of a simple feature.
So one question. So
yes.
Can the number of nuclei in the overlap be a feature?
Yes, of course. Yes, that can be a feature. Yeah, but eventually, okay. So, but what we have to be a little careful about is we should not just take the number of nuclei. You can always take it, but it's always good to normalize it. So maybe the number of nuclei divided by the area of the overlap. Right, so that can be a cluster, because that feature can be normalized across all the overlaps. Correct? Yeah. Okay. So what we did was, so back then we did not have fancy deep learning models. We just had simple convolutional networks. So we compared these handcrafted feature performance against against simple convnets, and our model performed a lot better. And we also saw that we could use these features to predict survival in these patients. And clearly, we see that the features were different for patients who survived longer versus patients who survived shorter. So what is this entire pipeline then? You start with your whole slide image. If you look at the left of the screen, you extract different kinds of features, and in this particular project, we looked at cancer nuclei and TILs. TILs are the tumor infiltrating lymphocytes, like we saw yesterday. So those are the yellow nuclei that you see here. Those are the TILs, and the blue are the cancer nuclei. So we first extract the patches, then we obviously segment the nuclei. That's always the first step, or mostly that's the first step when it comes to handcrafted feature extraction where you have nuclei involved. Then using some classification algorithm, you decide which of these cells are cancer cells, which of these cells are lymphocytes, and then after that what we did was a PCA, principal component analysis, to identify the top 20 percentiles. So principal component analysis is a dimensionality reduction method which gives you the samples where you have the most variance. So we decided to retain the tiles that had the top 20% of the variance, and then after that we took those tiles, did our graph based analysis, and did an average of we took different statistics of these features that we extracted from the bunch of patches, and then we did our analysis. And yesterday, if you remember, we had this discussion regarding how we have different kinds of stains. So H&E stains, yes, but then you have different kinds of stains that can stain for different kind of lymphocytes like CD4, CD8, CD20. So all of these have different functions. So you can also create these graphs. So there was a slide yesterday on compartment specific analysis. So here we did a lymphocyte specific analysis. So we created graphs, we created CD4 graphs, CD8 graphs, CD20 graphs, and then looked at those were the features that we used to distinguish between different groups of or different prognostic classes. Now, what was the takeaway from these experiments? So we see that when we extract the nuclei and we look at the overlap and we look at the intersection, the spatial arrangement of the cancer nuclei with respect to the lymphocytes, for the high risk case, we see that the lymphocytes are sort of spread out, but for the low risk case, we see that the lymphocytes are more dense. They're sort of densely arranged with respect to the other nuclei in this example. So what this says is that, probably because of the fact that the nuclei are very close to the cancer, the lymphocytes are very close to the cancer nuclei, there's some sort of an effect that they cause, or some sort of a mothering effect that leads to the low risk cases to being better receptive to therapy as compared to the high risk case. And these kinds of insights can be drawn using handcrafted features like these graph based features that you see here. So, is there a question?
I just wanted to know, like, how do we generate that image, like from the strain, like
this one?
the second one, like the coloring, the.
These are cell segmentations. So we took this image, we applied a segmentation model, and then we identified the contours of the different nuclei, and then the segmentation, it was a segmentation and a classification model. So we had ground truth of cells which were TILs and cells which were non-TILs, and we basically segmented and segmented them and assigned them to different classes, and that's what you see here. So the blue ones are the non-TILs and the yellow ones are the TILs.
Okay, so it's a separate model.
Yeah, it was a separate model.
So, but like, how do you generate the ground truth for this? Like,
so the ground truth was given by pathologists. So we sat with them, they annotated where the nuclei are, where the lymphocytes
I wonder,
are.
is that possible to like contour that each and every
So this was done almost 7-8 years ago, or maybe a little bit before that. So we had pathologists who sat and contoured it. Now you have many different data sets where you have these contours available. So you can use those to train your model. So some of these data sets are Munusac. So this was a data set that was put together by a group from IIT Bombay, Dr. Amit Sethi's group. Then you have another data set called PanNuke. So PanNuke data set has multiple different domains, multiple different cancers, and patches of multiple different cancers. They have the segmentations of the nuclei and different categories of nuclei. Okay. So this was, I believe, from the University of Warwick. So you already have multiple data sets like this available that you can use to train your model. Okay. But yes.
I mean, I wonder that, like, how it is possible to contour each and every cell.
I'm sure it took hours for them.
Yes.
But nowadays, so let's say that, that's a good question. But let's say that you have a different kind of cancer that you're working on, and you want to do this. What you could always do is you can start with some of these patches that are out there. You can start with some of these models, and then you can see how these models work on your data. Okay. Clearly, it will not do well because you have a different cancer. Yes. These were different cancers. But if it does at least decently okay, you can start identifying the errors. Like with uncertainty analysis, you can find which of these nuclei are incorrectly segmented and classified. Then you can only provide those nuclei to your pathologist and have them annotated. Okay. Right? And it's not necessary that you need to do that for hundreds of thousands of nuclei. I mean, even so, fine-tuning is possible with maybe a couple hundreds of nuclei. And we have seen that just by taking an existing model and fine-tuning it with new annotations from maybe 100 of patches, it starts performing a lot better.
Okay. Yeah. So it's not possible to like annotate the entire whole slide image. Is it?
It's possible. It's difficult. It's very time-consuming.
Yeah. Yes.
Yeah.
Thank you.
Yes. There's a question there.
So the image that we plot here, so all these are actually 3D images. So
no, 2D.
No. So I mean, they are originally 3D images, right? DICOM images.
No, these are not DICOM images. These are all pathology images.
Okay.
So pathology images can be stored in a DICOM format, but that standard has not been widely accepted yet. But these are 2D images. These are not 3D images.
Okay. So then, I think I was thinking how contours. I mean, drawing the contours in 3D.
Oh no. Yeah. So let's say that if you look at the radiology images that we saw yesterday, those are 3D images, right? I mean, that's a valid question. How can you draw contours in 3D? So you cannot really draw contours in 3D, but you can take multiple slices and draw contours in 2D, and then it becomes like a 2.5D, right? You will have multiple circles in different planes, and that essentially becomes like a 3D. So it's called a 2.5D. I mean, you're right. If you have a 3D structure, we would want a 3D contour. Tumors that you see in radiology are 3D in nature. Ideally, we would want a 3D contour, right? But how do you get that annotation? You get multiple 2D annotations, and that becomes a pseudo 3D. But the bigger cross section, it won't really pan 3D, right? It will still be 2D.
Yeah, right. Just to get the 2D information out of it. Like, so let's say we have the 3D, and in case of tumor example, if I have to let's say draw some these kind of features just to see where that they are dense or where they are sparse, right? So can't we just take the biggest cross section and then do this analysis on that? Or
I don't think I follow your question. So when you say cross section, what do you mean?
cross section as in like plane the
So
plane
let's say
cutting
this is a cross section, right? So there is a tumor, like a 3D tumor bulk, and this is a cross section that has been taken.
Yeah.
Right. So
and right that area, like that top 2D image that we are seeing from the top of that cross section, can't we work on that?
so yeah, so this is a cross section. So we are working on that.
Okay. So I mean, so ideally what we are saying is from the 3D image we have to extract the cross section and then get the 2D image and then do these analysis
Yes.
on top of it.
Yes.
Thank you.
Yeah. Sure.
So actually it is this, see, tumor is a 3D structure, and they do slicing when in the lab, and they take, they put it on a slide, glass slide. Yes, that is called histopathology. So in histopathology they do this typically. So if you have a certain volume of tumor, they would slice through different very thin slices, and they put it on slide like on a glass slide. So this is already a top view, and there might be multiple slides for a single tumor tissue.
Yeah.
That's it.
Thanks. Yeah. So what was interesting was that there are different kinds of features that we can compute, right? One simple measure can be till density features. By till density, what I mean is count the number of tills, normalize it by the area, you get the density features. So we see that so LUAD stands for lung adenocarcinoma, LUSC stands for lung squamous cell carcinoma. So if you look at lung adenocarcinoma, and if you look at the till density features, you see that the till density features were able to distinguish between the low risk and the high risk group. This is the p-value. But the till spatial arrangement features were not statistically significant. But for the squamous cell carcinoma, the spatial arrangement features were statistically significant, but the density features were not. So what this means is that for different kinds of diseases, you can have different kinds of features or different set of features that can help you achieve that same task. It's not necessary that you will have the same feature that can help you do task A and task B, right? So it's a horses for courses approach. So along similar lines, this was a work that we published a few years ago at ISB. So this was in lung adenocarcinoma. A lot of research that has been done in lung adenocarcinoma, people take these whole slide images, they tile them up, they extract features, and they say, okay, we have these sets of features, they are performing well for this task, that task, and so on. But what we showed here is that, yes, you can extract features from the whole slide image, but we should be mindful of where we are extracting features from. So for a lung adenocarcinoma, there are regions like these lepidic regions, acinar regions, micropapillary, mucinous, and solid regions. So these are all defined pathologically. So if you talk to a pathologist, they will tell you that these are the different kinds of appearances of the tissue depending on how the cancer looks like, how the spread looks like, if there is necrosis, some other kinds of presentations. Based on that, you can actually divide that whole slide image in a lung adenocarcinoma into lipidic regions, acinar regions, micropap and mucinous regions. And what we can do after that is, instead of blindly taking patches from everywhere, you can have compartment specific analysis like we did previously. You can extract features from your lipidic region, from your acinar region, and from whatever other regions that you have, and then you do your analysis, right? So what we showed was that if we followed that kind of a paradigm as opposed to combining everything together, our performance was a lot better in survival analysis. Okay, so now let's come to transparency in model attention. So here I'd like to explain why domain is important. Many of the foundation models that are out there, such as there will be some Dino based methods and other kinds of foundation models, you will see that when you take different augmentations of your data, and this doesn't have to be imaging data, this can also be data that you collect from sensors or other kinds of data. So if you look at where the model takes its information from, or where the model attends to when making a decision. So let's say that on the left you have this image, there's a bird that's sitting in on a branch and you have some leaves in the background. You apply your foundation model and you look at the model attention, you'll see that the model attention is probably in the region where the bird is. Now let's say we do some manual cropping. You crop out this region and now the bird is here. You'll still see that the model attention is sort of focused around the region where the bird is. Then you do some other cropping and then you do another operation like a grayscale operation and the bird comes here. You still see that the model attention is here. So what this means is that natural images are object centric. There is always, on most accounts, there is some object of interest in your natural images. When it comes to medical images, especially pathology images, there's not just one single object. There are multiple different objects. In this image that you see here, we have a lot of lymphocytes, we have a lot of cancer cells, there are normal cells. So there are many different kinds of cells here. So the model doesn't really know where to focus its attention on, right? So if you apply different kinds of augmentations, if you apply some, let's say, some intensity changing operation, then you have a grayscale operation. So, and after that, when you look at the model attention, you'll see that it's very random, it's here and there. And this has important repercussions in the downstream analysis, because if the model is not attending to certain regions, that means that when you perform your classification, you won't really have features or you won't really have representations from that region for your classification. But if you look at how a pathologist looks at slides, yes, there will be certain regions that are not interesting to them, but they will still look at those regions. Like they will still take information from those regions to make their decision. So what we did was we introduced a model, we introduced a module to slightly tweak the way these foundation models attend to these different regions. Now instead of something like this, the attention from our model, which we published a couple years ago, was like this. So you see how the attention is more sparsified. So it's a little bit well distributed as compared to the attention here, right? So that's what we did. And how did we do that? I won't really go into the details of this. Since this is pathology, we first used a cell segmentation model to identify where the cells are. Then we had a background. Since we have the cells, we also have the corresponding background. So typically in these self-supervised methods, you try to, so let's say that you have cancer regions, you have non-cancer regions. So what you do is you take patches from cancer regions and you take the representations coming from your foundation model, you pull those representations together, right? Because a cancer should look like a cancer. Now if you have background, you take your cancer representations, you take your background representations, you pull them apart, because cancer should look different from background. Now, that concept still holds, but what we did was, sorry, not background, cancer and non-cancer, sorry. So, what we did was, we had cancer, we had non-cancer, but we introduced the concept of cells and background. So, we took regions with cells and we pulled them apart from regions that did not have cells, and we took regions without cells, we pushed them together to regions that did not have cells, and also the other way around. So, we introduced another sort of a semi-supervised concept into the self-supervised learning that made these representations better. Now, our model, our tweaked model could focus on the different cellular regions. And here is a result. So, you see the different kinds of cells here. This is a model attention when you do not, like the vanilla SSL approaches that are out there, and with our SSL approaches, we can see how the attention is sort of well distributed. I mean, there are regions where you have low attention, but if you compare, these images, clearly our attention is more diversified. So, what that means is that our model can learn information sort of equally or equitably from the different regions that are out there. And how can we use this for downstream analysis? So, we take our whole slide images. So, this method that we developed was called DIRL, diversity inducing representation learning, and we divided them into patches, and we extracted our features based on our DIRL method, and then we clustered the features. So, what does that mean? So, we took the feature representations and we decided on k number of clusters, either using a k-means clustering or whatever, your favorite clustering algorithm that you want. So, you identified the clusters, and we had a very simple mechanism or a very simple way to construct these handcrafted features. Again, these are deep learning features, but we took these features and did something that was more handcrafted. How did we do that? We identified these clusters and we looked at, in that whole slide image, how many patches were cluster A, how many patches were cluster B. Right? So, we identified the percentage of patches belonging to the different clusters. Now, each of these clusters means something, that is why it becomes handcrafted, and I will show you why. So, this I believe we divided into 15 or 20 clusters, I believe 20 clusters. If you look at cluster 2 and you look at the patches that were in cluster 2, you see how they had similar appearance. And you look at cluster 13, you see patches that had, you see the patches in cluster 13 had similar appearance, similarly patches in cluster 4. And we went back to our pathologist, Dr. Raj Gupta, and he identified, or he examined these clusters and gave us the interpretation of what these clusters actually look like from his point of view. So, cluster number 2 had stroma and tumors, cluster number 13 had stroma and tumors, cluster number 4 had small black nuclei, and you can actually see these small black nuclei, right. So, this means that these clusters that we found using, or that we computed using the technique that we developed, these clusters mean something from a pathologist's perspective, right. And for pancreatic cancer, so this was for basal cancer, or so for basal subtype of pancreatic cancer. This is classical subtype of pancreatic cancer. We see that the clusters were very different, and you can see that cluster 20 you have these lymphocytic invasions, cluster number 18 you have some other kinds of presentations. So, now we know what these clusters are. That is why we created this handcrafted feature representation, which looked at the cluster preponderance or the cluster fraction in each of the images, and just use that as a method for a classification. Does that make sense? So, how we use both deep learning and then extract more handcrafted features from it? Okay. Yes.
How did we select the clusters, like 1, 4 and 13, how that got?
No, so what I am showing here is random. I mean, you can, a paper which is currently under review, we do an analysis on all the clusters. So, what I am just showing here is a few representative clusters. And so, if your question is how do we decide the cluster number, it depends on you. You can select 3 clusters, 5 clusters, 10 clusters, but eventually we would, I mean, it's good not to go, there are only so many patches that you have, right. So, it's good not to go beyond maybe 25, 30 clusters, because then it also makes your task more difficult. You have to sit with a pathologist, identify what's what is the commonality between the patches in each individual cluster, but we stuck to 20 clusters.
Okay.
Okay. So moving on. So these are some of the foundation models that are out there. So like I said, foundation models, the initial set of foundation models that were published were using mostly natural images, but it has been found and it has been shown, and you can also try those out for yourself. If you apply these foundation models for medical imaging tasks or for tasks in medicine generally, you will see that they don't do well. So what it means is that we have to train foundation models with medical imaging data, and that's what a lot of these papers did. FICON, Uni, Conch, Virchow. So a lot of these models were trained on hundreds of thousands of whole slide images, and these models do a lot better than foundation models that have been trained on non-pathology data. So yes, so there are models everywhere, right? Now every 2-3 days you will see a new foundation model coming out. But the question now is, how do we bring in interpretability to this foundation model? So there was a question yesterday from one of you saying, you have deep learning, you have handcrafted features. How can we bring the best aspects of both of them together, right? So, and there are methods to do that, and our lab has been pursuing and researching what these different kinds of methods can be. So, and why do we need to do that? Because deep learning over the last 2 to 3 years or over the last half a decade has been shown to be really good when it comes to many of these tasks involving big data. So, the performance of deep learning model is much better in many of the use cases compared to the performance of traditional machine learning methods using handcrafted features. However, as we have seen in the last few slides, deep learning methods, the feature representations that come from these deep learning methods are sort of black box in nature, because we don't really understand what these representations are. But for your traditional handcrafted features, we know what is the meaning of these representations. So the traditional way of interpreting, so eventually we would want to go from a black box approach to a glass box approach, where we know what kind of decisions we are making and how we are making these decisions. So traditionally, when you want to classify a whole slide image, you would apply something called a multiple instance learning method, and we spoke a little bit about this yesterday, where you take different patches, these are bag of patches, and using some attention mechanism, your model tells you which are the patches that are more important or most important, and then what happens is you do this attention visualization, and this is a post hoc analysis. You can tell after you apply your model and your model gives you a decision, you can take these patches, show your attention to your clinicians and tell them that this is where the model focuses on, this is where the model does not focus on. Can you please tell me what's going on in these regions? So that's the traditional way of bringing in interpretability to the deep learning methods. However, these visualizations are often hard, and they're sort of subjective for experts to interpret. Like if you provide these high attention regions, it's not that visible here. If you provide these high attention regions to your doctors, to Dr. A, they might tell you something different from what Dr. B tells you, right? So it's a little bit subjective in nature. So we want to move away from that subjectiveness to something that is more objective. So this is a paper that we published in CVPR 2024, I believe. If I remember correctly. So this is a conventional MIL. So where you show these high attention regions and low attention regions to your clinicians and ask them to interpret what these patches are. So the method that we developed was called self-interpretable multiple instance learning, SIMIL. So what we did was we had a combination of deep learning approach and handcrafted approach. Now your deep learning features would be something that you get from your deep learning feature extractor, which can be any foundation model or maybe a deep model that you have developed in your lab. So what we did was we extracted the nuclei using the nuclei segmentation models that are out there, and we extracted different kinds of morphometric descriptors, shape-based descriptors, different spatial proximity-based descriptors, and now we had a collection of handcrafted features. Now we trained a multiple instance learning method which took into account both the deep features and handcrafted features, and the handcrafted features were used to ground the performance of the deep network. Now, the results that came out from the model, yes, we had these patch attention mechanisms. We could still show these patches to the doctors, but we could also tell them what are the features that were responsible for the model calling it cancer A versus cancer B. Now, we could tell the doctors that it is either tumor cellularity that drives the prediction or necrosis that drives the prediction. So, this has some degree of explainability to it, right. And I'll talk a little bit, I'll talk more in detail about how this method is in the next project that I'll talk about. But here are some of the results. So, you have the whole slide images. This is for IDC. IDC is invasive ductal carcinoma of the breast. Yes. Yes.
Sir, like the generation of handcrafted features,
yes,
like it also requires one model, right? Like
yes, yes, yes. It requires more. It's a model. It requires a lot of time.
That's what. Like
yes.
So before that generation of that the cellular things like as you previously said, so we have to use some model to generate that handcrafted features.
Yes.
Sure.
Right. Yeah. Yes, and you have to generate this not just in training but also in testing, right. So, you need to compute this, and that's why this is a little bit time consuming, because we need to know what these features are and then use that to co-train the deep feature extractor and the handcrafted model. Yeah.
Okay. Are we involving any pathologist after generating the handcrafted pieces to just to validate that features?
Yes, yes, we are doing that. We are doing that. I'll show that in the next slide.
Okay.
Yeah.
Thank you.
So, IDC is invasive ductal carcinoma of the breast and ILC is invasive lobular carcinoma. So, you see the patch attentions where we have regions with high attention and low attention, and these are red ones are the neoplastic cells, green ones are the connective cells, and blue ones are the inflammatory cells. And we see that how the patches, the high attention patches that were found, we clearly see a different expression of the of how these different cells are arranged in the IDC versus ILC. And when it comes to involving pathologists, what we did here was we showed the features that came out of it, and these were the features that were important, and they looked at these features and basically told us that these are indeed the right features that the model is picking. Right. So, you have certain arrangement of the neoplastic cells, you have mixing of connective cells in the neoplastic regions, and so on and so forth. But if you look at some of the terms here, skewness of the cells, right, and there will be some standard deviation, there is some graph modularity. Yes, these are interpretable, like you can explain to them with some math formula, some descriptions of what these features are. But if you think about it, these are still difficult to explain, right. I mean, imagine you go to a doctor telling them that a graph modularity feature of XYZ gave you this prediction. They'll be like, okay, what are you talking about? I don't know, right. So, it makes sense for us, because as engineers, this is something that we can develop and we can explain to ourselves what it is, but it becomes to some extent a little bit difficult to explain to clinicians what these features are. So, what is the solution here, and what do they understand? So, by the way, before we go to that part, here are some of our results. So, if we include, so this is our self-interpretable MIL. So, our self-interpretable MIL was a lot better, or at least similar in performance to some of the other methods, with the added advantage of the interpretability. So, okay, for some reason the quality is not that good. Anyways, so this was the follow-up work on this SIMIL method, and this method was called GECKO. We just recently presented it at ICCV. So, clinicians or pathologists might find it difficult to understand what the different mathematical descriptors are, and what is skewness, what is graph modularity, and on these features. But what they understand are these features. What is keratinization, what is lipidic growth. And if you look at the pathologist reports, you will find terminologies like this. and when they make their decisions or when they diagnose a certain condition, that will be based on these concepts. So now our goal was to see what if we change that traditional handcrafted approach and bring in something that pathologists can understand better. So we wanted to bring in whole slide level concepts. Now how do we identify these concepts? So by the way, what we did here was, so let's say we want to distinguish between lung squamous cell carcinoma and lung adenocarcinoma. So the first step was we identified about 50 to 100 different publications at reputed places. We took these publications that we're talking about, that we're discussing or that had characterized what was the pathologic presentation of squamous cell carcinoma and adenocarcinoma, provided them to a large language model like ChatGPT, and asked the model to summarize and give us 20 different concepts that are representative of squamous cell carcinoma and representative of adenocarcinoma, right? Because we wanted to have an exhaustive concept bank. Now we went to our pathologists and told them, this is what ChatGPT gave us. Can you please clean it up for us? Can you tell us, okay, out of these 40, 50 concepts, give us the 10 best concepts which you think are representative of adenocarcinoma and squamous cell carcinoma, and that's what they did. So they gave us the, so we took the language concepts or the pathology concepts. We provided that to a vision language model. So a vision language model has two encoders. It has a vision encoder, it has a language encoder. So we took the image or the patches from the image, we gave that to the vision part of the VLM, we got the embeddings, and we took the language concepts, gave that to the language embedder and got the language embeddings. And then we aligned the two embeddings coming from the vision part and the language part. And this is how we trained the model at a very high level. And here are some of the results from our model. So this is a lung squamous cell carcinoma. This big or this long ID that you see here is the TCGA ID. I just left it there, so in case you are interested, you can go into TCGA, you can download this slide and see what it is. All our models are public, by the way. So at any point, if you want to use these models, if the works are published, the models are public. So these are the top K patches that the model found or that the model determined, and what our model tells us is not just these top K patches, but it gives something that's called a whole slide level concept activation. This is the part that makes it interpretable. So what we can tell the end user or the pathologist now is that, so this was a LUSC case. So we tell the pathologist that these were the concepts that are overactivated or underactivated, and because these concepts are overactivated, the model calls it a LUSC or an LUAD, right? And it can tell them that these are concepts that are underactivated. So these kinds of pathological insights is something that we can provide to these to end users, which is not possible with just foundation models alone. Okay, so that was our contribution in this work. So this is what the model tells us: high activation of XYZ, low activation of XYZ. And then if you want to further simplify it, you provide this to another large language model, like you provide this to your ChatGPT model, and the model tells us that 2 out of the 3 activated concepts are classical, are very representative, highly representative of LUSC and directly reflects squamous differentiation. That is why the model is calling it LUSC. And if there are other concepts that are activated, then it would call it LUAD. So it gives you a result. It also tells you why that result was arrived at. Right? So that's our contribution here. So you see how we are using deep learning, but with deep learning we are making it interpretable. Similarly for LUAD, you can look at the slides that we'll be providing tomorrow. So top K patches, you have the different concept level activation, and you see how some activations, some concepts are highly activated and some concepts are have low activation, and based on the high activation concepts we can call whether it's LUSC or LUAD. Same, the model output, and then the model output is further summarized by a large language model, and you have a more sort of a descriptive and a more reasoning kind of an output coming from the large language model. Okay, so with that, we'll conclude the first lecture of today. Any questions?
Sir, I have a very basic question, sir. Sir, what if the two diseases LUSC and LUAD both are present?
Yeah, good question. Yeah, so a lot of times, so that's a fantastic question, because these many times, maybe not for LUSC and LUAD, but there can be other diseases where you can have multiple diseases present on the same slide. So what that would mean, so if that is indeed the case, then we would hope that the model will pick up concepts related to disease A and disease B on the same slide. And it will tell you that, okay, these are the concepts that are related to disease A that are overactivated, these are the concepts that are related to disease B that are overactivated, and then the final decision would probably rest on the clinician, right? But it can still tell you what are the concepts. Even if, let's say, even if the classification is wrong, the concept activation will be correct, right? So yeah, that's how we can do it.
Thank you, sir.
Yeah. There's another question here.
Sir, the interpretability technique that you have shown,
Yeah.
Is it developed by you or like I?
It's developed by us. Yes.
Achha, achha.
Yes. And you can actually read our paper. It's there in the bottom of the. So ICCV 2025. If you look up our work, you'll find it.
Okay.
Yes.
So like somewhere I have seen that TCAV, the testing with concept activation vectors, like somewhere.
So yeah, so
it's
there
like
are other kinds of concurrent works that are out there. They have explored different ways of interpretability,
Yes,
but
yes.
this part was actually developed by us.
Okay.
Yes.
Thank you.
By the way, Dr. Baig, I think there's some mistake in the timing here. We have to fix that. It should be 11 to 12 or 11:30 to 12:30. Yeah, fix that. Okay.
So any more questions? So I wanted to ask a few things.
Yeah.
So this foundational model, like what is the typical data size, data set size?
Yeah, so for the FICON and the Virchow models, they have at least 100,000 whole slide images, right? So that sounds like a low n or a low number of.
Sorry, you said 100.
100,000.
100,000. Okay.
Yeah, usually when you train foundation models, you'll need millions of images. So this sounds less, but since these are whole slide images, you further patchify them, right? So each whole slide image will have hundreds of thousands of patches. So eventually it's 100,000 times 100,000. So that's the number of patches that the model was trained on. Yeah.
Okay. So, all right. Another, have you come across any analysis as to, yeah, of course, like we always try to maximize the data set size, but what is the sort of
trade-off?
Yeah, trade-off.
Yeah, so there are multiple papers that have done that, especially in machine learning conferences. They have shown how certain foundation models have actually done well with limited data as compared to other foundation models, and they apply small tricks here and there, some data augmentation tricks, and based on that, the model performance can be better. And I think I have some of those slides in the second part of the lecture where I'll show how small tricks can lead to better model performance.
Okay. And one more thing, have you come across any foundational model which is also interpretable?
No, so that's something that we are trying to bring in. I mean, like he said, there are other concurrent works that do that, some concept level activation works, but I think we are just beginning to scratch the surface. It's very new. Maybe in the last 1 year you'll find 2 or 3 different works, but not many.
Okay. So just to summarize, like what exactly a foundational model is. So in simple language, we can say that foundational model for a specific application is like a software. So anybody else can also use it without having to retrain it, right?
Yes. That would be the goal, because if, first of all, retraining or training a foundation model is a massive effort. And if you have, models that are out there that have been trained on, millions of data points, make use of that. So take those take those models and adapt them to your applications using proper prompting or fine-tuning techniques.
Okay. Any more questions?
You have a question? Okay.
So with this, actually, we wrap up the first lecture of the day. There will be tea break um, already there. So yeah, we can break for tea and then resume again at what is the schedule?
11:40. Let's do 11:45.
11:45.
So it's 11:30 now. 11:20 now. So 11:40.
Let's do it 11:30 so that we
Okay. So 10
go on
minutes.
schedule.
Sounds
On
good.
time. Yeah. Okay. Thank you. Thank you.
Okay. So welcome back. So so once you've settled, let's continue with our lecture on interpretable and generative AI in computational pathology. So in the first part of today's lecture, or lecture 5, what we saw was how we can the different kinds of techniques that we have actually developed to bring in interpretability to foundation models. So like we saw, there are so many of these different foundation models that are out there, but these foundation models they lack in interpretability, in explainability. However, there are methods like these handcrafted feature engineering methods, or there are these concept-based methods, these concepts, or these language-based concepts that are more appreciated or better appreciated by clinicians. So how can we marry foundation models with more handcrafted approaches to make these integrated approaches more interpretable? So that's what we saw in the first half, or in lecture 5. So in lecture 6, we will be focusing on the generative AI aspect. So I mean, obviously, since in today's day and age of AI, a lot of things are centered around Gen AI, so it would be criminal not to talk about Gen AI, right? So we've been doing a lot of that in our work as well, not just in radiology, like you saw on day 1 of the GIAN series, where we showed how we can use some text-based prompts to generate images, and also we saw how we can infuse eye gaze patterns to make these generated images better. So similarly, we have also been working on different generative AI approaches for digital pathology as well. Okay, so I don't know if you'll get these slides, so you can always scan this, and you'll see our GitHub repo for a lot of our work that we have done on Gen AI. That's not exhaustive, but those are some of our published works. So one of the challenges in computational pathology that we discussed yesterday was out of focus areas, right? So similar to that, you have problems like low resolution image. What does that mean? So one of the first steps of getting a slide digitized is, mounting that slide, or preparing that slide or preparing the tissue on your glass slide, sticking that into your scanner, and then getting it digitized, right? So this scanner, end of the day, you'll have like a microscope, you'll have different objective lenses, right? So end of the day, what you have is you have different powered lenses, and based on that, and that would decide what quality or what resolution that slide has been scanned at. So like we saw yesterday, you can have slide scanners all the way from 5x to a couple 100x. The better the scanner, or more high resolution the scanner is, the more expensive it is. Right? So we want to make sure that we have, I mean, obviously it's good to have high resolution scanners, but it's not always practical. There are cost issues. Not all centers might be able to afford these scanners. However, there are basic versions of the scanners that are at low resolution, which, let's say, a digital pathology center should be able to acquire. Now, let's say that we have an image that has been taken at 5x, right? And we saw that in the foundation models, and there was this question yesterday, what resolution do we train these models on, like 5x, 10x, 20x, 40x, 50x, whatever. So if you have a model trained on 20x images or 40x images, but the images that you have right now that are collected at your digital pathology center, that's only at 5x, we can apply a 20x trained foundation model on 5x, but obviously the results that we get will be suboptimal, right? Because these images were trained at different resolutions. What does that mean? Should we throw these images away? No. We can still use these images. And how do we use these images? There are techniques called super resolution techniques, where we can super resolve a lower resolution to a higher resolution. So today I'll be talking about, or in this particular work, I'll be talking about some of the GenAI methods that we have developed to super resolve low quality, low resolution images to high resolution images. So this was published last year in Medical Image Analysis. Before this, there were multiple different works in generative adversarial networks, or GANs, that had done that. But if you want to get into GANs and generative AI, you'll see that GAN methods have their own issues. Where there's mode collapse, a lot of times you cannot really work with high dimensional data and so on and so forth. A lot of that problem has been solved with diffusion models. So diffusion models are essentially models that start with noise and progressively denoise it, and then you get an image from it, or you get a denoised data from it. I won't really go into details of how diffusion models work, but what diffusion models let us do is, one of the important or one of the flexible approaches there, or one of the functionalities that diffusion models have, is we can condition the diffusion models with multiple different kinds of conditions, and these are called conditional diffusion models. So the goal is to go from an image what you see on your left of your screen to an image what you see on your right of your screen. Now, so by the way, if you look at these images and you have different kinds of primitives here, what is the difference that you see in the low res image and the high res image? Anyone? Show of hands. So what are some of the visually, what are some of the differences that you can observe? Everyone can observe this difference. Okay, can we have a mic here, please?
The edges are blurry.
The edges are blurry, yes, good. On the left image, right?
Yeah.
As compared to the right. What else? Behind you, Shomajitya.
The morphology is more clear for the cells.
Morphology is clear, so you can see the cells clearly.
Yeah, and also the staining, we can see the staining properly, like which are more dark and which are light. So
Yes.
based on that, the nucleus positions and all this, that can
Yeah.
be
Good.
told. And also another thing, the proximity of those cells, like from left side image, it is not clear the proximity of the cells, like two cells, their distance between them.
Right.
But from right side, it is very clear to see the proximity of those cells.
Right. So that again ties back to the first answer, the edges of the cells. So because the edges are clear, you can clearly see how close the cells are with respect to each other. And you're right, you can actually observe, the shape of the cells, the morphology of the cells, the texture of the cells, right? So if you look at this one right here, I don't know if this is a cell or not, maybe it's a gland, but you can clearly see that you don't see the texture well here, but you see the texture quite clearly here, right? And if you want to apply your not just your foundation models on this image, not just your foundation models, but you also want to you want to apply your handcrafted features, it's very difficult to expect that your handcrafted features will be able to extract something meaningful here. You don't have the you don't have the shape of the nuclei, you don't have the structure, you don't have the texture. I mean, if you don't have that, you can't reliably identify the centroid of the nuclei, which means your graph methods will suffer. So everything breaks down, right? So in order to make sure that that does not happen, the first step is we super resolve the image and then apply our techniques on the super resolved image. So is that clear? So why we need super resolved image or good quality images? Okay. So moving on. So what we did was we trained a super resolution technique, and then these are some of the results that we got on prostate cancer and on lung cancer. And I'll talk about what's happening here. So if you look at, so HR stands for high resolution. So these are the original high resolution images. You can clearly see that the structure of the nuclei is quite clear. You see what's happening with the other tissue regions and so on and so forth. You see the dark nuclei here. So for the for the lung cancer case, but these are the low resolution images in the second column. So the goal is to develop techniques that can take your low resolution images and generate these high resolution images. So that's what we want to do. And like I said, there are existing methods, or there were existing methods back then, and these were mostly based on GANs, generative adversarial networks, that could do this. And you can clearly see that these methods have been able to super resolve these images quite well. And here are the results of our method. And since they look so similar to each other, it's obviously difficult to appreciate the quality directly by looking at this. I mean, obviously you can look at the difference between BSR GAN and our method, or BSR GAN and SWIN-IR GAN. It's quite clear that it's quite blurry here, it's less blurry here. But eventually we would want to quantify it, right? If you don't quantify it just qualitatively, it's difficult to say which method is better. So one of the metrics that is used to quantify, for those of you who are from signal processing background, you would be familiar with the concept of signal to noise ratio, right? So you have a particular signal, and then you have a noise. You can always look at the signal to noise ratio, and then higher signal to noise ratio is usually good, right? Another metric that is used, or one of the most common metrics that is used in generative AI is called FID. So it's called a Fréchet inception distance. So using the FID scores, we can actually quantify how good the generated image is. However, the case I'd like to make here is, some of the existing methods like PSNR or SSIM. PSNR is peak signal to noise ratio, or you have SSIM which looks at the structural similarity. So these might be methods, or these might be metrics that are good for real images, or not real images, for natural images, but these are not methods that are optimal, or these are not metrics that are optimal for pathology images, and I'll show you why. So same thing, we have low resolution images here, we have high resolution images here, and here you have different kinds of super resolution techniques. So bicubic interpolation. So bicubic interpolation is a very easy method. So you basically take pixels and you interpolate the values so that you get something that's closer to, let's say you take an average of pixels or something like that. So it's a very simple method. So, and you clearly see from a visual perspective, the bicubic interpolated image looks worse than our image, right? The image that we have super resolved. I don't know if this is clear here, probably not. Maybe you have to look at the YouTube link. I think you should do that now just to appreciate it. So this is very visual. When it comes to Gen AI stuff, everything is very visual. So if you look at it closely, and you'll see it in the slides tomorrow, the bicubic interpolated image is hazy. I'm assuming some of you can actually see it. It's hazy, and our image that you see here, it's quite clear, or even some of the images that have been generated by the GAN methods, they're quite clear. But look at the signal to noise ratio. So the bicubic interpolation method has a signal to noise ratio of 27, and our method or some of the GAN methods have signal to noise ratio that are lower than that, right. So this means that something is going on where, even though perceptually the GAN based methods or the more sophisticated methods look better, but from a quantitative perspective they don't, right, which means that this tells you that there is something going on with the evaluation metrics. Now here's again, like with a number of other things that we have spoken about over the last 2 to 3 days, there's an important lesson. You will be using different kinds of metrics for your analysis, but make sure you understand what these metrics are, because for your purpose, for your evaluation purpose, those might not be the best metric. And don't just go with metrics that people have been using without really understanding, because there will be times where you know that your method is performing well, but your metric does not reflect it, and this is a classic example of that. So what we did was, first of all, we realized that this is not the best metric to go with. So we needed to design better domain specific evaluation metrics. And in our case, the evaluation metrics or the domain that we needed to design this metric for is digital pathology. So when it comes to digitized pathology images or these histopathology images, what are the different objects of interest? You have the nuclei, you have, let's say you have the stroma, you have the epithelia, you have other kinds of glands and whatnot, but eventually everything comes down to nuclei and background, correct? So it's important that when you generate these super resolved images, the texture, so you mentioned that the texture was bad, or you mentioned that the edges were not clear. So we want to ensure that the super resolved images are as close in texture and shape as possible to the super resolved images should be as close in shape and texture as possible to the real high quality images, right? So that's the eventual goal. So in order to achieve that, what did we do, or what was our metric? So we have the high resolution image, we have the low resolution image. So if you're interested in working with these images, there are models out there like HoverNet, which I briefly mentioned a couple days ago, and there are other models, more recent models like CellVIT. So you can take these models and you can extract the location of the nuclei, you can extract the boundaries of the nuclei, and this is what it is. So you extract where the nuclei is. So the white regions represent the nuclei and the dark regions are essentially the background, and you can overlay the nuclei boundaries on the high resolution image. And then you have your low resolution image. We use our method, which is, so this was a previous version, it's called SuperDiff now. So we take that method and we super resolve it. So ISR is the super resolution image or the super resolved image coming from the low resolution image, right? So you can clearly see that this looks very similar to the high resolution image. Now what we do is, we take the nuclear segmentations that were obtained from the original high resolution image and transfer it to the super resolved images. Ideally, if the reconstruction or if the super resolution works fine, the location of the nuclei should exactly be the same, right? The location should not change, right? So if this is the low resolution image, this is the corresponding, this is the high resolution image, this is the super resolved image. If a nuclei is in this location here, it should be exactly in that same location. The location should not change. So that's why you take the locations of the nuclei from the ground truth, you overlay the locations to the super resolved image, and you look at if there is any change in the intensity or if there is any change in the texture of the nuclei, right? So if the images are close, then the changes or the, let's say, the interhistogram distances between the intensities and the texture will be very small, like they will be as close to each other as possible. So which means that that is a metric we should use for our analysis rather than signal to noise ratio or some of the other metrics. Okay, and that's exactly what we did here. So then we compared our state of the art GAN methods against our method, so which was SuperDiff, and we had different GAN methods. We had the bicubic interpolation method. We applied it on different cancers. We had prostate cancer, lung cancer, brain cancer, and we had different data sets as well. We had 100 cases here, 2000 cases here. So based on that, if you just focus on the texture, so L1 is essentially a distance metric, right? So you have two different points. You just look at the L1 distance. So if you look at the L1 distance with respect to texture or intensity, lower the distance, the better it is. We find that our method was a lot better compared to the GAN methods. Okay. Now, how do these generated images look like, let's say, not for super resolution image, but for another application where you want to generate synthetic images? So remember, we had this discussion where we saw that if you do not have enough training data, one of the ways in which we can augment our training data set is through generative AI, right? So you can use certain conditions, you can generate these synthetic samples, you can provide these samples to your deep learning model or to your machine learning model, and you can train this with real samples plus synthetic samples with the expectation that the new model will be better than the model that saw a very limited quantity of data, right? And that's one of the applications. I'll talk about that in the next slide, how it was useful. But here's just a representation, an example of how well we could do this. This was a workshop paper at MICAI 2023. We used a diffusion autoencoder for generating these images. On the top row here, so this entire block is colorectal cancer. On the top row here, you see real examples of different types or different categories or different let's say subtypes of this colorectal cancer, where you had normal mucosa, lymphocytes, or different regions rather. These are not subtypes. Let's not call it subtypes, because when you call subtypes, it means that there's some molecular subtyping involved. It's just the different locations. So you have lymphocytes, you have mucus, you have smooth muscle, stroma, tumor, and then the second row, what we show here are synthesized examples. Now just compare the first row to the second row. You'll see that the second row, the images that we generate are quite similar to the images that you have on the first row, and these were verified by our pathologist. So if you look at our paper, you'll also see we have a small section there where our pathologist talks about what they think the differences are between the two sets of images, how similar they are, where we are going wrong, and all of that. So you'll see that section there. But at a high level, you can see that we have been able to do a good job in synthesizing these images, right? And that's not true for just colorectal cancer. The model that we trained, we also had examples of breast cancer as well. And you see that here, for breast cancer, we had normal cells, we had metastatic cells, and you see that we have been able to generate it quite well. So now, how do we use it? So what's the downstream analysis that we performed on this data set? So this is a Chaoyang data set. It's freely available. If you want to work on simple classification problems, I would recommend you to just look up this data set and see if you can train these models. You can apply foundational models, you can extract features and run simple models to distinguish between normal. So it has, I think, 4 categories, normal, serrated, adenocarcinoma, and adenoma. So feel free to play around with this model. So back then we picked this model because it had multiple classes. So it was a good model to start with, but nowadays you have, it was a good data set to start with. Nowadays you have you have larger data sets. Yeah, but anyways, so the goal was to see if we could train our model on the training set and evaluate it on the test set to distinguish the 4 different categories that you have here. Now, look, if you look at the table, so there's something very interesting happening here. If you train the data, if you train your model, your classification model, I don't really remember the specifics of what classification model we used. It's there in the paper. So you take the features from your feature extractor, provide it to your model, and if you train your model only on the real data and evaluate it on the test set, you see the performance of the model in the first row. So just look at the numbers there: 78, 78, 47, 92, 68. Right? Now, we applied our synthetic, our Gen AI model and generated the synthetic samples. The next model that we trained was only on the synthetic data. We did not use the real data for training the model. Now, if we use only the synthetic data for training the model and evaluate the classification performance on the test set, which was all real data, you see the performance in the second row: 75, 72, 46, 91, 67, right? So what do you observe? What's happening here? Like, what's different between the first row and the second row?
It has almost on par performance with the
Yeah, so if you could just use your mic.
Yeah, so the model trained using synthetic data has on par performance
Right.
with
So
the real data.
yeah, so it's, even though it's slightly lower, we can see that it's quite well, it's coming quite close to the model performance, to the model that has been trained on real data. So what this tells us is that the synthetic data has actually captured some of the phenotype, some of the phenotypic properties from the real data, and that is why we are able to achieve performance that is quite close to the model performance that was trained on the real data. Now, interestingly, if you combine the real and synthetic data for training, so you take the training data set, the training data set that has the real samples, you augment that data set with your Gen AI model. So you have now generated samples, your synthetic samples, you combine the real and synthetic data for training and then evaluate it on the real test set, we see that there's quite a significant jump in performance, right? Look at the third row. So what this tells you is that even if you have, let's say, so one of the questions that I get, and I'm sure many of you will have this question if and when you get into machine learning: how much data is enough for training? Like, I've been in this field for more than a decade now, more than 15 years now, close to 20 years, but I don't have that answer yet, right? So we don't really know how much data is enough. It depends on what the clinical problem is, or what the problem is, what the classification problem is, what the detection prediction problem is. Sometimes data points in the order of hundreds might be enough, and there will be times where even with thousands or tens of thousands data points, you might not even get good results. Okay, so doesn't matter what it is. What this tells you is that if there is a scope to augment your real training data with something that, with your synthetic data, which obviously has to look similar to your real data, it cannot be something entirely different, that could potentially be an avenue to augment your data set and potentially lead to better model training. Another lesson here is look at the distribution of the training set, or look at the distribution of the diseases in the data set. So you have what, 1000, 800, 1400, 600, and then 700, 300, 800, 273. So clearly the adenoma case, or the adenoma class here, has fewer samples compared to the other classes, right? So there's a class imbalance here.
So I have a very basic question.
Yes, go ahead.
So we should take a macro average or a weighted average, while calculating the F1 score, or precision or recall. Because
right.
I think this is a weighted average, right?
Yes. Yes.
We should take weighted average or macro average, because in macro average is very less. When you compare to from weighted average to macro average.
Right. So that's a very good question, and I'm glad that you brought that up. So it depends on if there is actually a class imbalance or not, and depending on that you can decide what to take. right. So, most of the results that you see here are all weighted averages that we are showing.
So like should we provide like two?
You can provide both. You can
both.
provide both. Yes.
Because
And
like most of the papers right now also like they are only putting the weighted average.
Right. And the other thing, so that's with your F1 scores. If you are reporting accuracy or AUC, report that, but you should also report something called balanced accuracy.
Balanced accuracy.
Right.
Like,
balanced accuracy, balanced AUC. That's when you actually. That's when your metric reflects the class imbalance. Right. So yeah, that's a good point that you raise here. Yeah. So it's clear that we have some level of class imbalance here. Now, if you look at the performance of the model for adenoma, you see that when you combine the real plus synthetic, and I'm talking about this column here, you see that the performance improvement for adenoma classification improves significantly. So, what this tells you is that for cases where you have severe class imbalance, you can apply GenAI techniques to artificially augment the data set, and hopefully your performance will increase. Right? And this is especially true for these less represented classes, because we do not have enough samples to train our model. Okay. So, next we'll see how we can use another modality associated with pathology, and that's called text. So, similar to radiology, where we have radiology images and we have the corresponding radiology reports, with pathology we also have the images and you have the corresponding reports. And in the reports, what you have is the pathologists basically look at these images and look at, it's not just one slide. Since it's a chunk of tissue that has come out, you section it, there will be multiple sections. So, they look at multiple sections, and based on what they see, they come up with a consolidated report. So, TCGA doesn't just have images and omics data, it also has text data, by the way. So, you can look up, just fire up TCGA on your browser, you can look at you can look at some of the text reports that are out there, and you'll get an idea about how these reports look like. I have some examples later in my slides. So, whole slide images are accompanied by extensive pathology reports. So, what we do is we use these reports as global level conditioning information about the image. So, these reports will tell you what's happening in the image as a whole. I mean, they might have some information as to, okay, this is, left side of the image shows something, or the right side of the image shows something, but there won't be any annotations per se, right? It's a report. So, it's all in text format. So, this report will give you a global understanding of what's going on in that image. Now, obviously, pathology, like we saw, it's so much information. You have, if you remember, we zoomed in yesterday, starting from a local scale to a global scale. At the local scale, you saw the texture of the cells, the shape of the cells, the morphology, and as you keep zooming out further, you'll see how these cells are arranged with respect to each other, and then you zoom out further, you start to observe how the shape of the whole slide image is, right. So, you have different levels of information. So, which means that if you patchify them, if you patchify the data set, you divide it into tens of thousands of patches, because these are huge images, and if typically when you look at deep learning models, you'll have patch sizes like 224 cross 224 or 512 cross 512, usually around that range, nothing bigger than that. So, if you have patch sizes like this, and these images are 50,000 cross 50,000 images, you can have so many patches from these images. Now, let's say that you have trained some sort of a patch classification model where you are quantifying the amount of till in every patch, or the amount of, let's say, necrosis in every patch. So, from there you can get a patch level information, and from the reports you can get a slide level information. So, the idea behind this project was to combine patch level information with slide level information to build a generative model. Okay, and I'll show you how we do that. So, first, for the slide level information, we get the report, the pathologist report, and it can be a very detailed report, or it can be a short report. Sometimes lot of times it's in a structured format. There are CAP guidelines, Association of Pathologists, so they have those guidelines. If they follow those guidelines, then you'll have a more structured report. Otherwise, a lot of times these reports can be free text. There's no structure to it. It'll be just like them explaining what's happening there without context. So what I mean by structure is that, let me ask you this question: what's the difference between a structured report and an unstructured report? Anyone? Any guesses? Structure and no structure. What does it mean? There's a hand there.
Like there is some sections and there is some entry points where you have to enter some value.
Right. So if you look at, let's say if you've ever looked at blood reports, you'll see that there'll be certain sections and the values get filled in there, right? As opposed to, let's say, maybe back in the day when you did not have structures like this, there'll probably be a sentence saying that, okay, your cholesterol level is this, your sugar level is this, something like that, right? So it can be either in a structured format or an unstructured format. So whatever format it is, you can provide it to a large language model and you can get a summary. So the large language model will summarize it for you, and you can ask the large language model to summarize it for you in a way that all the reports, when it summarizes them, they follow a similar structure, right? You can create your own structure. That's what I mean. So let's say that you create your own template and you ask the ChatGPT, you ask your large language model to take that report and fit it into your template. That's all we did. And then, so that was the slide level information. Next comes the patch level information. So I showed this slide yesterday where one of our colleagues developed a tumor TIL classifier, where we had we had a model that would quantify how much TILs or how much tumor each of these patches had, and based on that we just did a a dichotomous thing: high tumor or low tumor based on some threshold that we chose, and high TIL or low TIL. So each patch had these values. So maybe 1 0 0 1 1 1 0 0, right? So let's say tumor TIL. So TIL low, TIL high, TIL high. So basically high low, low high, high high, and low low, right? So it's a very simple thing that we designed. So once you had that, so this is basically what I just spoke about. So now you had a patch, you had patch level information and you had whole slide level information. So you can provide this information as a conditioning strategy to your diffusion model. So diffusion models, you can condition them with information like this. And we did that, and based on that we generated the output for each of the patches. And here are some of the results from a quantitative perspective. So we achieved state of the art in image quality. We surpassed some of the previous efforts. FID, if you remember, I introduced the FID concept, where FID is used to evaluate how good the image is. So lower the FID score, the better it is. So we were able to obtain an FID score which was lower than some of the other methods. And interestingly, when we combined the slide level information with the patch level information, so if we did not have the slide level information, the FID was high. If we combined the slide level information, the FID was low. So this means that entire context means something, that when maybe the pathologists also tell us something that is not directly visible in that image, right? Some sort of conclusions that they draw based on what they see in that image. That is not there directly in that image, correct? So just an illustration of what's there. So here's the report. So here's the report from TCGA, and this is the prompt that we gave to the LLM, and the LLM generated an output like this, and then we asked it to make it more succinct, right? We asked it to summarize it, and this was the result. This was provided to the language embedder. We got the embeddings that was then used as the slide level conditioning. So here are our results, qualitative results. We see on the top row you have the real samples, and then in the second row we have the path LDM, which is our method, and we can see that results the generated patches look quite similar to the real patches. Then back then we only had 3 methods, or 2 methods rather, for comparison. So med diffusion and this one. And we showed that our method was quite better compared to these other methods from a qualitative perspective as well. And one of the things that we observed with other methods is that there were a lot of artifacts. Again, these artifacts can be brought about by in many different GenAI methods, and our methods did not have these artifacts. So this is also interesting because most AI methods, most GenAI methods will have some sort of artifacts or the other. I'm sure that if we did a detailed analysis, our methods would also have some artifacts, right? So what this means is that when we evaluate or when we apply, when we train our GenAI methods and when we are validating it, this again falls under that category of error analysis. So identify what these misclassifications, what these artifacts are, and look at these artifacts, compare these artifacts with artifacts that other methods develop or show you, and then maybe also sit with your clinical collaborator and talk to them, ask them to interpret what these artifacts might be. This might be just nonsense artifacts, but maybe there's something you can learn from that as well, right? So this is also very important, which a lot of research works don't do. Okay, so what we saw in the previous project was we took these representations coming from the reports, which is at a whole slide level, and we take these representations coming from the patches, which are essentially classifiers that we trained, and use these representations, the slide level representations and the patch level, whatever till tumor scores that we had to condition our GenAI model. But this might not be feasible always, right? Maybe you don't have a classification model or you don't have reports, which means intrinsically this data becomes unlabeled, right? So now you have unlabeled data. How can we still train a GenAI model to do what we want to do? So how we do that is by using our foundation models. So we have the foundation models that you saw previously, PhyCon or Virchow or Conch or some of these other models. So when you apply, when you run your patches through the foundation models, you will get a representation, right? So now you can use that representation to condition your diffusion model. You don't need to have a till tumor classification, or you don't need to have a textual description of what's going on in that image. You have your foundation models, apply your foundation models, run your your patches through the foundation models, and you get the representations, you get the embeddings. Those embeddings become conditions to your diffusion models, and we did that here. So based on that, we see that the quality of images that we got were quite good, and it represented. So we basically, what we do here is we propose using the representations learned with self supervision in place of human annotation. So this was what I just discussed. So this can help us learn to synthesize images that are similar both in appearance and semantics of the reference patches. So just an observation here. So a lot of this, in fact, what I'm explaining to you here is using images as examples, but you could do this with any modality of data. If you have text data, if you have sensor data, you can use all of these techniques to do this, to essentially augment your data set. So by that, what I mean is, so let's say that you have an array of sensor data. You can, if you have foundational models that have seen sensor data, you can extract representations from your sensor data. You can then use these representations, you can use these embeddings to generate synthetic sensor data. And now this synthetic sensor data can be used to, let's say, fine tune your model or further refine your model. Okay, does that make sense? Okay, we also had other projects, another project where we tried to do a multi-scale generation, because we know that single scale is not enough. So we can have representations at 5x, at 10x, at 20x, 40x, and so on. So we can always take contextual information through foundation models that have been trained at different resolutions and provide multi-resolution embeddings as conditions to your diffusion models. That's what we did here, and we have a multi-scale generation technique. So using the multi-scale features, we can boost the performance of the multiple instance learning tasks that we saw in the first half of today's lecture. So here's some recent work. This is currently under review at Nature BME. So here we are. So for the first time, we proposed a foundation model from a generative AI aspect. So it's a generative foundation model for digital pathology images. The code is out there. Feel free to look it up. So what you can do is you can take images and then you can use our proposed framework to generate synthetic images. And we also have made the dataset public. So we have 1 million patches that we have synthetically generated, and you can use these for your model training. So there is another aspect to it that's very important. A lot of times, so how many of you are familiar with the concept of federated learning? So some of you here, right? So a lot of times, when it comes to collaborations, so let's say that you're developing your model here at NIT Rourkela, and you have your collaborators somewhere else, let's say on the other side of the continent, or you have, let's say, even collaborators at hospitals elsewhere. For some reason, they don't want to share the data with you. I mean, obviously, sharing of data it's not straightforward. There's a lot of ethical issues there. In the US, we have this HIPAA considerations. There's patient privacy information, and a lot of legality there. And a lot of times it gets very tricky to share data, share images, or share any medical data. So federated learning, just a very high level description is, you don't have to share data. What you can do is you can share model weights. So let's say that that there are like these three rows here, and I'm an aggregator. So each of these 3 rows have their own data. So you train your model, you train your model, and you train your model, and you send me the model weights. Don't send me the data. Send me the model weights. I have some sort of an aggregation strategy. I will, using whatever aggregation strategy I have, I'll combine these model weights, and I will push updated model weights to each of you. And then with those updated model weights, retrain your model for the next, for the next bunch of epochs. You will have new model weights. Send them back to me. I will now update them, and obviously I have a validation that is running on my side. When I'm happy, I will tell you that this is my final model weight. Use it on your side, right? So you don't have to share your data with me. Just share your model weights with me. So that's a very very high level description of what federated learning is. Now sometimes even that may not be feasible, right? Even federated learning may not be feasible. So then what I can do, so let's say that 3 of you are collaborating. So what you can do is you can take your real data and using some Gen AI techniques, generate a synthetic version of your real data and share it with your collaborator, or share it with me if I'm your collaborator, right? You can do the same thing. Generate a synthetic version of your data and share it with me. So you are not sharing the real data. You are just sharing the synthetic data with me. Okay, so that's something that can be done as well. And we have actually shown the feasibility of that in this paper. So this paper actually we used close to, there was a question regarding how many slides are enough to train a foundational model. We had about 70,000 slides, and this was a model that we trained. We had multiple different cancers here. So the other thing about foundational model is that you don't need to stick to just one kind of domain, one kind of organ, right? So we had about 10-15 organs that were represented in this foundation model, and this is where we are illustrating how we can do privacy preserving synthetic data generation. So similar to federated learning pipeline, and other things that we have shown that could be done using this foundation model is stain translation. We have taken H&E stains and translated them to ER, PR, Ki67 stains, basically IHC staining. So virtual staining using our foundation models. Okay, so there is something else that is important here. yes, we can take the representations that your foundation model representations, use that to condition your diffusion models and generate synthetic patches, but like we would hope, and obviously some of this is happening, that these foundation models, in some sense, because you have different layers of your neural networks, they will encode the nuclear layout, the morphology in some sense, right? We don't know how it is happening, but it is happening. But how about we explicitly give that as a condition, right? So by that what I mean is, you on the left of in the first column you see centroids, which can be essentially the centroids of the different nuclei, or they can be centroids of other primitives. Can you use the centroids as conditions to generate your image? That's what we did here. We just provided the centroid and we asked the model, okay, can you take this centroid map and generate for me a patch of breast cancer image, right? And that's what it gave me. What you see here is that you will see that the nuclei are exactly in the same position as the centroid map. Now, there are obviously multiple uses here. Let's say that for certain cancers, the topology or the spatial layout of the cells looks very distinct from another cancer. Now, you want to use it as a teaching tool. So, you can take that topology, that layout, and ask the model to generate multiple examples with that same layout, right? So, you can use that as a teaching mechanism, as a teaching tool for pathologists. And what you can also do is, if there are multiple kinds of cells, and that's what you see in the third row. So, you have neoplastic cells, you have inflammatory cells, epithelial cells, and so on. So, it's a multi-class layout condition generation. So, that's what we have shown here. Okay, so some of you here are working with transcriptomics, right? So, what if we can actually infer the molecular state of a tumor directly from the histology image? So do you have questions? Okay. Yeah, I think you should take a seat, Samajit. Yeah. Yeah. So yeah, so that's what we wanted to do here. So a lot of times okay, so why would we want to do this? Now you can give the mic. Yes. Why do you think something like this will be helpful, inferring the molecular state or the omics directly from a histology image?
It will give you the level of the gene, how the tumor is progressing. You will get that idea also. Generally, if you have just the genomics data, you don't get how the tumor is progressing.
Okay, so that's yeah, that's true. So since you have two levels or two modalities of data, you can do some sort of association. What else?
So typically, it's easier to, if you are able to train a model which can infer the genomics. So genomics is more expensive in terms of, yeah.
Right. So like you already know, it's very difficult and very expensive to get this kind of data. Even if you have facilities here to let's say take tissue samples, you might not have sequencing capabilities. You'll have to ship your tissue out somewhere else. They'll do that. They'll send it back to you. So what if, and we briefly discussed this yesterday, so what if you can do this on site? So if you have your images, can you use your images or can you use your tissue to directly infer the molecular state? So integrating gene expression with histology can give us information regarding both cell states and morphology, and eventually this can help in improving risk stratification and help in better treatment planning. So here I would like to introduce the concept of spatial transcriptomics. So usually in your genomics, in your transcriptomics data, you have a bulk level sequencing where you have your omics data is representative of the entire sample. But with ST or spatial transcriptomics, you have omics data corresponding to each patch or each spot of the image, and this is more granular compared to bulk level sequencing. Okay, so you will see that there's a lot of research going on ST right now, because this actually helps you quantify the heterogeneity of the omics profile in a given tissue. So predicting the spatial gene expression from routine histology, it can enable scalability, low cost molecular profiling, and eventually we would want to get to discovery of image-based biomarkers without sequencing. Okay, I don't know why the quality here is low as well, but anyways. So there are a lot of baseline methods where you have image encoders and then you have gene encoders. So you'll see that there's a lot of tools out there, a lot of techniques out there that have used transformer-based backbones to encode gene representation. So one of them is called a DNA BERT. DNA BERT, it was actually developed by a faculty, a group in our department. So what it does is you can take your expression profiles, provide it to this BERT model, and it would give you the representations. Anyways, so there are this and there are other models out there that can take your gene information, encode it, and then to develop a model you can do a contrastive learning between your image and your gene representations, and then when in your inference stage you can only have the gene information, or you can only have the image information, and you can predict the gene. So this is what a lot of methods have done. But for those who are actually working with gene data, you know that these don't work in an isolated manner. There's a gene-gene interaction, which leads to different expressions of different pathways. You probably know that better than me. So what we want to do is, when we train these models, we want to take into account the interaction between the different genes. And one way of doing that is understanding what the pathways are, right? So what we wanted to do here is, instead of doing, so Moinak was also involved in this paper, so instead of performing this contrastive learning at an image and gene level, we wanted to perform it at an image and pathway level, right? Because we know that these pathways are eventually what drives the pathogenesis of the disease. How did we do that? We took our images, we patchified it, we provided it to an image encoder, which can be any foundation model. We got the embeddings, we got the projection using some MLP head, and we also had the gene expressions. We did a gene set enrichment analysis. Then after that, we identified the pathway scores, and we did a pathway embedding. We again had a projection, and then we did a contrastive learning between the projection coming from the image head and the projections coming from the pathway head, right? And in the inference stage, we had only the image. The image would then be provided to a gene MLP and a pathway MLP, and it would compute the gene expression scores and the pathway scores. So that's the model. So this was just recently accepted at VACRI. It's a conference, it's a computer vision conference. So how can we use this? So we can use this, now we have, let's say, a foundation model that has seen what pathway scores are, how they relate to images. Now we can use that for downstream survival analysis instead of just image only models. Okay, so there are data sets, and you see newer data sets being added right now because ST is a hot topic nowadays. So we used this HEST 1K data set, which had not many samples, couple hundred samples, in fact less than that. So breast cancer had 36, skin cancer 12, lymph node cancer 24. But still there was enough data for us to train a model, and if you're interested, you can always look up this data set. Before this, the models that had been trained or that were out there to do gene expression prediction were STNet, His2ST, BLEEP, and MCLSTX. So these four models, and these four models did not consider pathways. And we saw that when we considered, or when we took into account the pathway scores for our contrastive learning, we found that the performance and the metrics that we used were the Pearson correlation coefficient, the MSE, and the so absolute error and the mean squared error. So these were the different metrics that we used, and across the board for breast, skin, and lymph cancer, we see that our performance was much better compared to models that did not take pathways into account. So what this tells us is that just the nature of the disease, just the nature, just how biology works, they don't operate at a single gene level. You have gene-gene interactions, because of which you have upregulation, downregulation of different pathways, and that leads to a disease progressing a certain way. So, if we take that information into account to the best extent possible, I am not saying that this is the only way you can do that, that has been shown to improve performance of gene expression classification. Qualitatively, on the top row you see the pathway scores, and on the bottom row you see the gene scores, and ST is important because again you have these scores for each spot in the data set. So, you see that, okay, so let me start with the gene scores first. So, this is the ground truth, and this is second one is ours. You have the other methods here. We clearly see that our method, the expression scores, obviously in a visually it's quite similar to the expression level of the ground truth, and you see that not just for the gene here, and the gene that we considered here was this one, which serves as a marker for immune activation, and this is one of the genes that is that's there for the hallmark allograft rejection pathway, and that's the pathway score that you see on the top part of the screen, and you see how ours is quite similar to the ground. I'm not saying it's perfect, and if you look at the quantitative scores, you'll see why, you'll see that that's reflected there. PCC of 0.58 is okay. It's not great, right? But it's still better than the other methods. Similarly, it's still quite low, but it's similar to the ground truth, at least from a relative expression perspective. This is another gene which is a marker of stromal activation, and we see how that gene, the expression level is quite good for our method compared when you compare it with the ground truth, and the corresponding pathway here, which reflects the aggressive tumor behavior. Any questions? Okay. So, what are the takeaways? So, we propose a pathway based representation of ST data, and this can enable biologically enriched embeddings for multimodal learning. And you see how the theme of interpretability keeps coming up again and again, right? I mean, yes, you have interpretability at the gene level, but if you talk about it from the pathway level, clinicians start to understand it even better, right? Biologists start to appreciate it even more. So, we designed this multimodal framework. It combines this transformer pathway encoder, an image encoder, and contrastive learning to predict both pathway and gene expression scores. And we evaluated it on multiple different data sets, and we showed how our method, which we term Pearl, it outperforms the other existing approaches. So, now what we are doing is we are extending this to a pan-cancer setting. So, the models that you showed there, they were individually trained for the different cancers. So, now we are trying to come up with a way to combine different cancers and come up with a true foundational model for gene prediction and pathway prediction. Okay. So, reports, coming back to reports, I know that I have been switching back and forth, but this is more recent work, unpublished, but we took part in this MICAI challenge and we scored the 3rd position. So, this challenge was about taking slides and generating reports from it automatically. So, there are many different methods, I mean not many different methods, there are a handful of methods out there that can do that, but what we wanted to bring in was, yes, we can use foundation model representations and use that to generate reports, but we wanted to bring in some interpretability, and in this case, since we had our published work Gecko, we wanted to see if we could use Gecko to bring in some concept level interpretability here. So, the objective was, given a whole slide image and short pathology report pairs, can we develop machine learning models to generate these text reports? And this is a data description, 7 different tissue types. They were collected from 5 different institutions, and this was from multiple different countries. This was actually organized by a few hospitals in Asia. Here are the different, and this data set is again public. You can always use this data set. So, you have the different organs, stomach, prostate, lung, colon, cervix, bladder, and breast. These are the number of cases. And for different organs, you had different diagnostic categories as well. And the goal was to classify the tissue into these diagnostic categories. So, you needed to classify what organ it was, what was the diagnosis, and something else. I'll look at that in the next slide. Yeah. So, here. So, two samples. The first whole slide image on the top, it belongs to colon. What was the procedure? I mean, that's not really necessary to be denoted in the report, but they had it, so we had to train a classifier for that. But this is not that important. You had the procedure, you know how it was taken, and then what was the diagnosis? So it was a tubular adenoma with low grade dysplasia. And for the second one, it came from the breast, a sono-guided core biopsy, and the type was invasive carcinoma. It was diagnosed by the pathologist, grade 2. Sometimes there might be other kinds of grades like mitosis, nuclear grade, tubule formation, and so on. So it was, so bottom line, it was a very heterogeneous data set. Okay, so it was not a similar level of information for all the diseases. So how did we approach it? First, we extracted visual features and integrated it with a transformer encoder decoder network for generating these reports. We use multiple different foundation models. So the reason we use multiple foundation models to encode the imaging representations is because all these foundation models are good. You'll see that, you know, some foundation models outperform the other on certain tasks, other foundation models are good on other tasks. So which means that they are capturing in some sense some complementary information. So we wanted to see if we could take these different information and come up with something that was reliable, that was robust. And we also used concept grounded features from Gecko, and after that we used some perturbations to come up with some agreement logic. I won't really talk much about that, but I'll show you the overall architecture. So you had the whole slide images, you divide it into patches, and then you apply different encoders, like I said. So conch encoder, this was developed by Dr. Faisal Mahmood's lab from Harvard. They're actually one of the you know, really good groups when it comes to developing these methods. They have access to a lot of data. They have a lot of models that they've made public. So a lot of researchers actually use their models. They use their models. So this is a conch model. The architecture is built on a VIT backbone, a VIT large backbone. There was another model called the Titan model, which is a multimodal model. So conch is, so Titan actually, I believe it used gene and images. So that's why it's a multimodal model. And then we had a Gecko model. Gecko uses what? It uses images and text, right? So it uses the concepts that we discovered. So you have these different representations, and then you provide it to a MLP adapter and mixer. So it basically comes up with a consolidation. It combines these different representations that are coming from these different models. And after that, there's encoder decoder framework, which was inspired by another work called MIGen. And then we use that to predict or to generate the text. So Gecko, I don't need to introduce that further. This is how it works. I had shown that to you earlier. Now, how did we identify this concept? So we spoke to our pathologists, or we provided, like I said, we first provided we identified literature, provided them to large language models, identified these concepts, and cleaned these concepts up by discussing with pathologists. So these were some of the breast-related concepts on the top: the cribiform pattern, papillary structures, and lung-related concept, lepetic growth, keratin pearls, prostate, cribiform, and so on and so forth. So I'm not saying that these concepts are perfect. We are still working on refining these concepts, but eventually we would want to get to a point where we have concepts that can actually describe these diseases to the best extent possible. Now, so on top in the red text, you see the ground truth data for a particular case. It's a prostate biopsy. The diagnosis was acinar adenocarcinoma and Gleason score. So Gleason grading is what is typically done in prostate, which tells you how aggressive the disease is. So synoptic report is a format where you can actually make it more structured, right? What's the biopsy site? Prostate. What's the mode? Biopsy. What's the diagnosis? Acinar adenocarcinoma with Gleason grade 7. What's the tumor volume? 90%. So right. So you take an unstructured format and make it into a more structured format. And on the lower left side, you see what our model predicted. It's you see that it's quite good, just that there was some difference in the Gleason pattern, but it was pretty good, and we scored we stood third in the final leaderboard. Okay, so here there was an interesting lesson here as well. I'm pretty sure that the model that we developed, we would have outperformed the other model, but there was some mistake that we did. So in the first round of evaluations, our model scored very poorly, like we were like 6th or 7th on the leaderboard, and we couldn't figure out what was happening, because we saw the results, we like qualitatively, by qualitatively I mean that we saw the predicted reports, we saw the real reports, they looked very similar to each other for a bunch of cases. We had no idea what was going on. Then, so this my student who's working on this, Suryakant, he figured out that there was some metrics, there were a few metrics that they used to evaluate, right? And these metrics are more NLP based metrics. Our results were all in small case, or the first letter of the word was in capital case, and the ground truth was all in small case, or something like that. So there was a case difference, and that led the metrics to fall drastically, right? So which means that when we trained our model, what we should have done is we should have converted everything to lower case, and then also the reports, the generated report should have everything in lower case, and then we should have evaluated it, right? So we did not, it was a very silly mistake, but it cost us. So, right? So these are the kinds of pre-processing steps that you have to make sure you do before you train your models. So these were the different scores, Rouge, Meteor, similar to what we saw for radiology. We have the same similar scores for pathology as well, and these were the performance of our methods. Okay, now how can Gecko improve it? So this is what you get from, this is the generated report that you get, that it's a breast tissue. The biopsy was a core needle biopsy. The diagnosis was a ILC or lobular carcinoma in situ. You have microcalcification, so on and so forth. Now, using Gecko, we had seen how it can tell us what are the top activated concepts, right? Now, you can provide this to your LLM with your generated report, and you can ask it to generate a more like an enriched explanation. Right. So now what you see is, yes, we can provide you the reports, but we can also provide you additional explanations as to what sort of features your model actually picked up on, what sort of features, what sort of concepts were overactivated. I mean, for all you know, these might not be useful for pathologists. The pathologists will still stick to this kind of a report. But from an interpretability perspective, like for us, we know what were the features that led the model to calling it a particular disease, it diagnosing a particular class, and so on. Okay, so coming back to QC, so one of the QCs, so why I have this QC slide here, it was actually motivated by that error that we made, where the lowercase, uppercase thing. So garbage in is garbage out. We have to make sure that our data sets have been properly quality checked before we provide them to our machine learning models for training. So there are models out there such as HistoQC, which was developed in one of the labs that I had worked previously. So when you look at histology slides, we saw that there can be out of focus areas, right? And there can be other things as well. So a lot of times what happens is when you prepare the slides, you will have crack on the slides. And when you digitize it, that crack looks bigger and it blurs certain regions, right? So, and when if you don't consider this in your model training, and if you provide the patches that have cracks and say that it's a cancer patch or it's a normal patch, obviously the model is learning from those crack pixels. It's not learning from the actual underlying tissue image. Similarly, interestingly, I've heard from one of my colleagues that there was a hair that went into one of these slides, like while they put the slide cover on, and that seemed like, okay, it was a part of a tissue, right? So these things need to be removed. There can be air bubbles. These air bubbles can be confused with, I don't know, some glandular structure or something, right? So we have to make sure that these portions are removed, or if you have methods like superdiff or other sort of correction methods, try to apply these if possible. So similarly, there are methods that people are developing, CTQC, there's a MRI QI or QC. There are other methods out there that can be used for quality control of radiology images as well. Okay, so coming back to our immunotherapy response prediction project that we have been seeing over the last 2 days. So we saw how we can extract radiomic features or radiology markers, but we can also extract pathology features, right? So we can extract where the lymphocytes are. We can look at how the lymphocytes are, how the cancer cells and lymphocytes are co-located with respect to each other. So what we did here is that we did a correlative study, and we saw how there are certain radiomic features that are associated with pathomic features. So the reason we did that is, because we want to get to a rad path setting where we can tell the doctor that because of certain expression patterns of the pathology of the primitives that you see at the pathologic length scale, that is reflected on the radiologic length scale. Right? So it gives us like a multimodal rad path setting. So that's what we want to eventually get to, a rad path synergy. So with radiology, what do we have? We have a larger field of view because it's a more macro sort of a picture of what the disease is. You have better anatomical and better functional characterization, and you get progression information. Now in pathology AI, you have better spatial resolution, you have more morphologic and mechanistic information, and you have better molecular insights. So finally, we would want to get to a rad path synergistic AI where we can do a true cross-scale characterization, which can lead to a more comprehensive phenotyping. So you have imaging information, you have pathology information, you have omics information, you have like transcriptomics data. So you can combine all of this data to come up with a more holistic description of what that disease is. And eventually, we hope that it can lead to improved workflow efficiency. So with that, again, thanking all my lab members and the computer vision group. Questions?
Any questions? I like the name, Rad Path. I also like the concept of linking these two together, because traditionally they are kind of different domains and disciplines. Okay, so we'll stop here for the for lunch, okay, and resume after lunch. So after lunch we have a hands-on experimental session. I think the links have been circulated to download the software and other things, so please download those. We will assemble here again at 2. So that we can start on time our experimental session at 2:30. Okay. Start time 2:30. They will come at 2 p.m. Start time 2:30. Okay. Thank you all. Thank you all very much. Session is again a hands-on experimental session. So I hope you had fun yesterday in yesterday's experimental session. I hope you understood and you took benefit from it. If you have any doubts from the previous session, you can also ask it today. So in today's session, we'll go a little bit, you can say, we'll turn up the notch, we'll turn up the regulator a little bit, and we'll go one level high. So in today's session, mostly we'll be covering medical image segmentation. So you all have downloaded the 3D slicer software and all the images. Very good. So we'll look at cell segmentation, lung segmentation, and you will get to try it out on a patient data yourself using the code that is being provided to you. So do you remember MedSam? It was discussed in lectures before, MedSam. Yeah. So it's a foundational model for slicing, medical image slicing. Then you can also train your own model, and then finally you can look at the applied side of machine learning, deep learning, which is image classification. So in this image classification, there are two classes, LUAD and LUSC. So what is the full form of LUAD? Very good. Lung adenocarcinoma and lung squamous carcinoma. So these are two different types of lung cancer. So you can look at the WSI images, and you can do classification as well. So and finally we'll be introducing you to diffusion models. So I hope you have a fun session today. With that, I hand it over to Manak for further discussion.
Thank you very much, Professor Baig, for introducing again. Okay, so just to confirm, like I'm audible till the last, right? Okay. So I'll start so let's start with any questions if you have from previous sessions, or if you are able to download 3D slicer and the folders that I have shared, session 2, everything is downloaded, we're ready? Okay, great. So same thing, I think you should have access to this folder. So let's start with cell segmentation. So just download this IPython notebook or open with Google Colab. So I'll just open my personal Google Colab here, and okay, so for today's session, you will need, like for almost all the notebooks, you will need to have GPU access. So I'll just, so just to reiterate how to change your runtime type from CPU to GPU, you'll have to click the runtime here. The file name is nitr underscore session2 underscore cell segmentation.ipynb. And to change the runtime type, you'll have to click runtime, click change runtime type, and then click the T4 GPU. I hope it's already selected, but for people who somehow it's not selected, just click this. Okay, so today so in today's lecture, we saw how Dr. Prasanna showed some histopathology slices where you have the cell segmented. So we'll do a hands-on on how to actually segment the cells. I think somebody had a question, what's the difference between the normal whole slide image and the whole slide image with those green colors. So here we'll learn how to generate that. So first we will install this GitHub repo, the cellpose.git. You can also go to their GitHub repository and try to see all the things that they have. This was, I think, if I remember, like the first cell pose paper was published in Nature Methods, and since then they had been updating their method. And cell pose is able to, like, segment different types of cells from across different stains and like, different cellular or different tissue types. So this is a good, I would say, segmentation algorithm, which you don't have to write too much code. If you have the histopathology image or whatever image that has cells in it, pre-process it a bit, and then you can use this code to generate your own segmentations. So yeah, like today we will just see how to segment some basic cells, but if you want, if you are doing some project which requires some advanced input output operations, you can always take a look at the GitHub code. So given that we will be running on Colab, so we don't have to necessarily worry about this, but in order to run, like, the cell pose code on bigger images, you need to have a good system with some high RAM and high memory. And this is like, very well tested on Windows and Ubuntu, a bit less well tested on Mac OS. So I think you can try out on all the 3 different systems. Okay, so the first step is you'll have to run this first step. So right now my session is connecting. It might take some time. It will take some time for you as well. So yeah. So one thing that I forgot to mention yesterday was, if you write any code, for example, A equals 10, B equals 20, and print A plus B, and that will give you the result 30. So here if you see, I just start writing A equals 10, B equals 20, but here when I start this command pip install, yeah, the output is 30. But here when I when I want to run this command pip install blah blah blah, I am putting this exclamation mark before that. Any idea why we are doing that? Yes, please, microphone. Yeah, someone was saying, yeah, just microphone to anyone.
So here using the bash terminal, that's why.
Exactly. So the cell remains the same. So this box is called a cell or a kernel, and here you are running a Python code, and here you are running a bash code. But if you just add the exclamation in just before it, you can run both at the same time in the same editor. Well, this might seem very easy and illogical to you, but believe me, like few years back, if you are trying to do this, it will give thousands of errors and you will never be able to do it. But like now, given that people write bash commands, shell scripts, and Python commands and everything at the same, like they try to write everything in the same console or the same editor. That's why people have come up with innovative methods like just adding an exclamation and you can run this. So I hope everybody has installed this cell pose repo. Now we'll import some libraries. So yesterday we briefly discussed NumPy and matplotlib, but and these two libraries we can discuss later, not important for this deep learning task. But we installed cell pose here in this command. Now it's installed in your system, but you'll have to call it. You'll have to call the function. So that's why in the second line we write from cell pose import model, score, IO, and plot. And of course, like I mean, you can still run multiple other models in CPU, but cell pose only supports GPU. So if you have not changed your runtime type to GPU, this will throw an error. So I will rerun this. It will just, so this line just loads the model and it waits from cell pose. So you see the beauty here, you don't have to train cell pose, you don't have to write the code for cell pose, just 2 lines. One line you import the library, and the second line you load the model and its weight. So you see like this 1.15 GV, this is basically the model and its weight. Now just for visualization, I like we download some sample images, which is right there again shared by the cell pose repo, some cell images here. Let's download them and see. So it's downloading all the images, and then this matplotlib command will plot the cells. So you see the different cells here. I don't know what the cells exactly are, but people from biology background, can you explain what these different types of cells are? I mean, just to say I don't know the correct answer. So anyone? No? Okay, doesn't matter, maybe. So we just like from machine learning perspective, we have an image, we have the mask, we just want to segment it. Doesn't matter what the cells are, but if you are trying to do some downstream application, you need to know what the cells are. Even I need to know what the cells are if I am planning to work with cells in the future. Okay, so these are the images. Let's try to plot some masks. So these are the images, and okay, we'll come to mask later, because mask is basically the ground truth. Then I am just feeding the images to model, and this model.eval. So there are two things in deep learning. Like we will not do any deep learning coding here, but still just like hands on if you are training deep learning models in the future. You declare a model. Let's say you made your own custom model, and you name it something like this. Let me write a pseudocode here. Model equals custom model, and let's say you have a function so you have a model, and I am just writing flag equals 0, but let's say you have a deep learning model with multiple layer here. So here you call the model or declare the model equals custom model. So now in deep learning code, if you write model.train in PyTorch specifically, if you write model.train, I'm sorry, this means whatever happens after this step, like let's say so whatever happens after step 6 till step 12, whatever you are doing with the model is getting trained. So let's say if you are passing through an image, you are passing the weights, back propagating the weights using a loss function, whatever you are doing, the model is getting trained till model.eval. When you declare model.eval, that means the model stops training, and whatever happens after this stage, the model is just inferring. It freezes the weights, it is just doing inference. So I mean nothing to do with this code, but just quick insights. If you see a PyTorch code and if you see model.train and model.eval, it should immediately come to your mind. Model.train means whatever happening after this, the model is getting trained, and model.eval means okay, now the model is doing inference. It's not training it, the weights are frozen. So you can play with the model. So the same thing happens here, model.eval, and you pass the images and use 1000 iterations, and it outputs something. We'll see what these output are. So if in the future you want to work with like cell segmentation, and if you have, let's say, a set of or a data set for which you want the cells to be segmented, you can just use the first few lines of the code, and your cell segmentation will be done. But the most important part is how to visualize it, which will come after the inference is done. So we are almost at 54%. So just to state that the model is not getting trained here, it's just inferring. The weights are frozen, we are just doing inference here. There are multiple other cell segmentation methods as well, like I think today morning professor was discussing HoverNet, and I think there is another well, I forgot the name, but yeah, there are multiple other cell segmentation method. HoverNet is one of the most popular one. So these models that we are talking about only does cell segmentation, but they still don't do cell classification, right? So Dr. Prasanna was talking about if this is a TIL, like is it a like a cancer cell, or is it a non-cancer cell, is it a fat cell, is it a lymphocyte, what is it? So to classify what this cell is, there are different algorithms. Those are cell classification algorithms. These are just segmenting the cells. It does not matter what the classes are. Any questions on cell segmentation? So are you guys confident if I give you another cell image, can you run the inference? Okay, great. Okay, now let's start visualizing. So here, just to keep in mind, whatever images will see from now on, the purple color is the ground truth, that is the actual cell, and the predicted is the yellow. So this ground truth might have come from a pathologist or a cell biologist. Okay, so let's see. So can you see the cells now? Like it's very well segmented using this yellow boundaries. So these are nuclei. So any idea why we can just see the so nucleus is inside the cell, right? But where is the cell here? Why we can't? Why we can just see the nuclei here and not the cell? Any idea from people with biology or whatever molecular biology background? Sorry? Stains, exactly. Can you answer that? Like, can you explain it a bit more? What staining is, how it disappears the.
So we basically, I think, stained it through the through those stains, like which stains only nucleus, like DAPI and rest, and like it doesn't stain the cell membrane, so that's why it is not visible. So.
Exactly. So if because of some staining we can't see the cell membranes or the other organelles of the cell, we can just see the nuclei, or we just want to see the nuclei, cell pose also segments the nuclei. So it's like, although we call it cell segmentation, but it can also segment the nuclei. And then it can segment the tissues. Then live cell. So live cell is a data set which basically has cells which are like moving in the petri dish or whatever the environment is across time. It can also segment these cells very accurately. Although just a quick glance, so this ground truth is basically in purple. So you see there is some errors here and there. This purple is basically the ground truth. So it has missed this thing entirely, it has missed some section here entirely, etc. Okay, yeast. So this is yeast, right? People from biology background. No? This for what cell is this? Yeast. So yeah, it's very densely located. Cell pose can also segment those cells accurately, and then the omnipose, the fluorescent, deep bags, etc. So people with biology background, you can actually play around with these data sets. They are publicly available for free. You don't have to register or do anything. You can just like download them, train your own cell segmentation model using these images, and then use it for downstream tasks. Okay, so now I will try to load a 3D image, 3D cell, and so basically cell pose works for both 2D and 3D cell structures. So somebody had a question in the morning that these are 3D cells. So yes, the images that we showed in the morning, they are from TCGA. So they are 2D but different magnifications. Okay. So a question can be, I mean, I had this question when I first was trying to do cell segmentation. What's the application? Like, of course, Dr. Prasanna discussed a lot of applications after cell segmentation. You can create all those like graphs and extract features. What else? I mean, okay. Let me simplify the question. So, for live cell, the cell is moving or the cell is growing. In order to understand the movement, or so what's the movement of cell called? I think the term is cytokinetics. Sorry, what? Motility or something. So in order to accurately measure, so I mean you can see with your visible eyes, but if you want to quantify it, put a number to it. Okay, what's the rate, motility rate, or movement rate or growth rate? There has to be a number. So in order to put a number, you'll have to quantify it. So the first step is the cell segmentation. Okay. So now here what we do is we run cellpose 2D and stitch the masks because it's a big image. I think Dr. Prasanna did discuss stitching a bit yesterday, and I think you guys are familiar with that concept. So you understand in the back end what's happening. So you can use cellpose for that as well. And finally, these are like the cells divided across multiple patches. That cellpose segments it and then stitches the mask. So for example, you see like this mask is here, but I think the patch just below it will have the other part of the mask. So you'll have to stitch the mask and then finally bring the main segmentation mask. And so that's it. You can do all the visualizations with these cells. Any question? Yes. In which step?
Purple.
Purple, that is. That should be this one, right? Yes. Yeah. So does it say which line you are getting the error?
28, 29.
28, 29.
Yeah. Outlines, prediction. Name error.
Sorry?
Name error.
Aim error.
Name.
Name. Okay, so did you run the previous, can you run it once again from the top? So that name error means you might not have declared a name before referencing it. Can you also like, yeah. Anyone else getting the same error, like some error in this
No.
in this step?
Okay, okay.
No, right? It works? Okay, great. So name error basically means that you are trying to reference some name, but you have not declared it previously. For example, let's say I write A equals 10, B equals 20. So like this is cell segmentation plus Python tutorials. And then you try to write a column which will compute the sum of A and B. So def sum A comma B return A plus B, and then you just reference, you just call sum, let's say. So it says missing two positional arguments A and B. But now, so that means you'll have to either reference the 10 and 20 here, so it will return an output, or you'll have to reference A and B, but what's the problem here? Okay, let's say Cx and y, and name this x and y, sorry. So I am not running this, but I am still running this. So name x is not defined, that means it's a referencing error. So you'll have to first run it and then run this, and then the name will, the output will be 30. So this is the problem of this cell and kernel, this setup is called like Jupyter or kernel based compiler. If you are working on inline compilers, that means like you write the full code, have a python.py and then run python that .py file, you will not have that error. It's just like you might misreference something in this Jupyter lab or Jupyter notebook setting. Okay, any other question for cell segmentation? What is IPYNB, this one? What? Where is that?
After stitching.
Oh, after stitching. Oh, so this is just like like you can also name it anything. It's just a name. Like which plane I am trying to stitch. I just named it I plane. You can name it anything like X, Y, Z. There is nothing technical or clinical in it. Yeah. Okay. So the next thing is, what was the next topic? Lung segmentation. Oh, I already have. Okay. So we saw some CT images yesterday, right? So let me try to visualize it again. Okay, let me try to see if we have lung images in this one. No, there are no lung segmentations, but it's okay. We have some parts of the lung. Okay, so this has lung segmentation available. So now one of the like important application, or so for the first step is you want to get the lung segmented out for deep learning training or any downstream task. But another thing is, let's say if you have a tumor in the lung, you want to know which lobe it is in. So like any physiology, like or I don't know the exact term, like the branch of study that studies human anatomical organs, it's called physiology, right? Or human anatomy. Okay, so any anatomy guys, can you like name what are the 5 different lobes of a lung? It's very simple name. It's just like right upper, right middle, right lower. So it's nothing clinical there, but like yeah, you can reference it like this. So like it's very important to know where the tumor is located, because radiologist, when they get this CT, they find it there is a tumor, they would ideally like to write a note that the tumor is in the right upper lobe, or it's in the hilar region, or something like that, So can we automate this process of segmenting the lobes of lung? It's very easy. So these are basically the lobes. You see there are 3 lobes in the right lung and 2 lobes in the left lung. Okay, so we just install this library, pip install lung mask, and okay, before that yeah, you'll have to upload the CT image. Interesting. Let me refresh it a bit. Okay, so my CT is uploaded, and hopefully my pip3 install lung mask also works. Also just like try to have the runtime GPU, I hope it is, otherwise it will, oh no, it's the CPU. So change the runtime type, save it, it will just kill the process. I'll have to upload the CT and everything again. So I think this will still run. What happened? Yes, I mean, so this library can still work on CPU, but it will be very slow. So it's better to use a GPU. So change the runtime type to GPU, and then install this library pip3 install lung mask. So if you want to know the GitHub repo for this code, lung mask GitHub, let's see if I can find it. Yeah, it's basically this. Don't worry, I'll send all these links after the sessions are done, along with the data sets and everything. So this is basically the GitHub repository for this lung segmentation code. So nothing fancy here. It's just a normal simple unit. Oh, before that, do you guys know what a unit is? No. Unit. So it is a segmentation, like, yeah, the microphone.
It is a segmentation architecture, sir.
It is a segmentation architecture, definitely, but and it's called a unit because it looks like U. I can just show you the unit image. Yep. I don't know if it's visible or not, but is it visible? It's a bit blurry, right? But doesn't matter. You don't have to know what's written there. But it looks like an U, and the downside, like basically the descending part of the U is called the encoder, and then the ascending part of the U is called the decoder. So if you remember, yesterday we discussed ResNet, we discussed DenseNet. So if you just cut the unit from this, like, the bottommost part, the encoder is nothing but a ResNet or a DenseNet. And if you add another upsampling ResNet to a encoding ResNet, it becomes a unit. So very simple. So along the similar time when ResNet and DenseNet came, unit was published in MICAI, and I think in 2017, if I remember correctly, and this model seemed to outperform or perform very accurately for segmentation tasks. So that's why unit is famously known for segmentation. It's a very simple architecture, nothing fancy, but with time people just removed the convolutional based encoder and put a transformer based encoder, and that outperformed normal convolutional encoder, everything. But the unit, like for a segmentation architecture, this unit structure remains the same. We will try to look at a very advanced unit, which is, I would say, is one of the state of the art, the very famous state of the art, which you can readily use for your own segmentation purposes. So okay, coming back to lobe segmentation. So this is again a very simple unit trained on this LTRC dataset. You can download this dataset, train your own unit, can be more accurate than this one. You can play around with this, but like if you don't want to train your own lung lobe segmentation algorithm, just use this library. And the code is very simple. It's just like we use this exclamation mark again because it's an inline or a bash command. Write lung mask, then a space. Don't mess up with this space, otherwise you will get an error. And then similarly copy the path and paste it here, use inverted commas, otherwise you will get another error. The input, that is the CT image, that is the model path, and then it's the model path, and then it's running the inference now, and the output will be the lobe mask. Any question how to run this lung mask GitHub repo? So if you have a CT, mind it, it should be a CT image. So if you have a CT, you can just use this command or these two lines to generate your own lung mask. So meanwhile it's taking, like while it's taking time, can you, so this image we saw, okay, I'll come to that. Meanwhile, can you go to file, open a new notebook in Drive. So this is basically the third part, which is let's try. So we discussed cell segmentation, we discussed lung lobe segmentation. Now let's try the same lung segmentation algorithm on a new patient. So to do this, go to file, go to new notebook in Drive and click it. Let me know. I'll just take a break here, so that we can, like you are seeing this, you are running the Google Colab notebook, which is already written by me, just pressing shift enter or those arrows, but let's try to do something on our own. So let me know if we have to stop. You can you open the new notebook? It should say something untitled. For me it's untitled 22. That means like this is my 22nd untitled notebook that I have. We are good? Okay. So here, like you can either copy paste the same code, or basically like if you remember the code, because it's so easy, pip install lung mask and run it. Are you guys following, like opening the new notebook and everything, right? Everyone is following, right? We'll just take some time. They are following, right? Yeah. Runtime, if you want to run it slower, you can use the CPU, but I hope you will not, so change it to GPU. Yeah. Click runtime, change runtime type, select T4, GPU, save. And then let me see. Oh, previous one is running, right? Okay, so we'll wait. We have time. You can run with CPU, yeah. You can run with CPU. Yeah. And the next line of command is lung mask. So here what I would like you to do is, okay, let me also change the runtime type to just CPU. So upload this TS underscore CT. Can you see this? TS underscore CT. Just upload this. Although this does not have the full lung, but it will be a good experience to see what if we have just partial lung, how accurate this model is. And I am also doing it for the first time, so let's see. Like I have also not tried on this CT. So upload the TS underscore CT. It's there in the drive, right? Just I'm trying to be clear. In the folder it's not there? I think it's there. Can you try to re-download it? I have to refresh, so that means it's not there in my drive? Oh, after refresh it came. Ah, interesting. So I was willingly trying to not give you that that. Yeah, just download it. Like it should not take much time. And the code to run this lung mask is again an exclamation mark, lung mask, copy path, inverted commas, and paste. So don't forget the inverted commas, it will throw an error. So again Python, okay, I'll just give you some time, I'll not rush. Yeah. Yep, we are almost 51% there, so let's see. You guys are following, right? Like you can. Can you please repeat the error? What's happening? Which command not? Oh, did you install pip3 install lung mask? If says command not found, just rerun. Yeah. Or the spelling is wrong. Oh yeah. So the problem with pip libraries are, if you just make a spelling mistake, there will be another library with that same spelling mistake, and then you will think, yeah, it downloaded accurately and like it's not a problem, but then your actual code does not work. Yes, like I'm just waiting. Yeah, yeah, yeah. Yeah, so there should be some output file as well. So you can just name it like output 123.nii.gz, and more importantly, you need to have this thing. Model name LTRC lobes just after the destination path. Okay, let me just quickly check if my previous, okay, it's 72%. Anyone whose this segmentation is done? No, right? I mean, if it's not done for me, I'm hoping it's still there at some percent. Yeah, what's the error? Sorry, is there any error? No error, right? Okay. It's complete. Sorry, what? Lung segmentation completed? Okay. We'll just wait. Your computer is fast. Oh, sorry. LTRC lobes. Just try to see if the caps are in caps and the small letters are in small letters. Is there space and everything? So what's the error? So is this model name correct? There are 2 hyphens. So, yeah, my font can be different. So it's model, nothing fancy there. MODEL NAME. It works, right? Is it running? So I'm there at 94%. Like Just a show of hands, how many like lung segmentation is done? It's done. 100%, 100%. Okay. How about you guys? Like your lung segmentation, the first one is done. Done. No, I'm by done I mean like the running. This 94% is 100%, right, for you? Okay, for me it's 101%. So okay. So I have my lung mask with me now. It's stored here as lobe segmentation. I'll just wait for a few more minutes so that like all of you have the first code done. The next step will be we'll visualize these lobes. We'll download these lobes and we'll visualize it. Yeah. So bread and the first maybe the lecture of Python will be indentation error. You'll have to have space like in the correct places. You'll have to keep the capital and the small letters and the small letters. Don't start with numbers.
You guys are writing the entire code without having any space. Input space, output space, hyphen model name space, LP are city lobes that you have.
Yes.
If you are missing any one space, then it will not run.
And that is why I kept this live thing, because just running my code is easy. Writing with your own hands, even just these 2 lines, you will learn about how to write even basic codes. And even though running this is very easy, but let's say if you're doing this in your lab and you're not able to figuring out, and after multiple iterations you're like, okay, let's scrap this. I hate deep learning. So
once you have run, you will be able to see the output file on your left side.
Yes. So those who have like already got this 100% done, you can just like download it. So how to download it? Just click on these. I'll repeat it again. Just hover your mouse to this lobe segmentation. You will see this 3 dots. Click that. You will get download. Any doubt? Any doubt? Are you able to follow? Yeah, I'm talking to you. Sorry. Yeah. No, it's okay. Yeah. Yes. Anyone who is not able to download or segmentation is not done, or there are any errors. It's running, right? Yeah, we'll wait. But any error in between? No, right? So for everyone, it's running. It's running. Which one? The second one? The second one I will come back again, the live task. The live task I will come again, but let's like first try to finish this download thing. So just like forget about the live task now. Just let's see a show of hand for whom the segmentation running is done. It's not done? Little bit? Okay. How about you guys? Segmentation, that this thing at least is done? Done, right? Okay. So if it's done, click this 3 dots and click download. That's also done, right? Everybody has downloaded? Downloaded, right? Okay. Okay. So now open your 3D slicer. It might take some time to open 3. It's not opening? The last segmentation did not happen? Okay, my bad. Okay, we'll give you some time. like how is 3D slicer working for you guys? Like, can you open it easily, or it's taking time? For me, it takes time. I don't know. I'll have to throw away my laptop maybe or something. So upload. So okay, let me also close and open it again, because my CT is already there, so I don't want. Yeah, see, my 3D slicer is broken. Okay, it works. Okay, so the first step is, wherever you have downloaded this folder, drag and drop this CT. I'm just repeating it again. Drag and drop the CT here. Just drag and drop. So in the folder you have this ct.nii.gz. Just drag and drop. Just check if it's volume, like if it says volume here. If it says volume and if the CT is the correct path, click OK. Everybody can open slicer, right? No problem in that. So drag and drop. Drag and drop is also done. So go to the folder that you downloaded. Are you able to follow? Sorry, last. Are you guys able to follow? Okay.
Please download the output file. Do not open it in the Colab.
Yes, do not open in Colab. It's a nifty file. It will not open in Colab. So drag and drop. Drag and drop is done. Drag and drop. Uploading the CT is done.
Should be opened as a volume or a CT?
Volume. The ct.nii.gz should open as a volume. Okay. It should look like this. How about you guys? Can you open the CT? How about you guys? You can open the CT? No. So drag and drop the CT, and here it should be volume, and then click OK. Any problem with you? The image is different. ct.nii.gz. Did you scroll it a bit? Who is there? Okay, I'll maybe come there.
I have to open the output.
No, just the CT. Maybe close it and then open again. Yeah, please do not open the segmentation file, just the CT file. Any doubt? Like, can you open the CT? Right? Okay. How about you guys? You guys want to? Right now it works for you? Okay. Okay. So now I hope you guys have downloaded the lobe segmentation as well, right? So wherever it is downloaded, for me it should ideally be in the downloads. I don't know where is it. It's not in my downloads. Oh, it's here. Okay. So again, same thing. Wherever you have your lobe segmentation, just drag and drop. But this time it should not be volume, it should be segmentation. So you have this description and then there is a drop down menu. Rather than volume, click segmentation. You can follow? Last, yeah. Can follow, right? Yeah. Okay, and then click OK. So if you click OK, you can now see the lobe segmentation very accurately. Something like this. Can you see this? Like for everyone, it looks like this, right? No funny predictions, no, right? Yeah, sometimes, like, so once I tried to run my own segmentation model in a very low resource setting, so I did not train it fully, just to try out, and then the lobe segmentation was outside the lung. So yeah, I mean that's also a good learning, right? Like if you are segmenting lung lobe, it should never be outside the lung. So if you are trying to design a deep learning model, the first thing it should come to, there should be some criterias which we call in deep learning as loss functions. You can penalize the model for predicting the lobe segmentation outside the lung, right? For example, the tumor, if you are trying to segment a tumor, you do not know where the tumor is, it should not be outside the CT, bare minimum requirement is that. So you can penalize the model that it should not be outside the CT space, it should not be outside the lung, something like that. But yeah, everyone can see this colorful lobe segmentation. You got a very what? Okay, let me see.
I think
it's a very
for me
unique
segmentation
lobe.
is outside.
Maybe it will be published in Nature. Let's see.
I don't know what went wrong.
Oh, I see what you did. Okay, let's close this. The same, right? This same colorful, old TV not working type of signals. Okay, I got it. What's happening? So whoever might have got this, weird lobe segmentation which looks like a cathode ray TV not working, you have to just okay. So for them, just close the 3D slicer and then reopen it. So it's step by step. First, upload the CT as volume. So did it open for you? Like now? Oh, yeah, it's opening. It takes some time. Yeah. So first, upload the CT as volume. You closed and opened, right? You are already getting the error. Now I am talking about, yeah. And then you uploaded the CT again. Now upload the lobe segmentation not as volume, emphasizing it, as segmentation. If you upload the label as volume on top of another volume, that is where you get this, I don't know what the term for that thing is, but I will go ahead with old TV not working type of segmentation. Okay, as segmentation. It's working for you now? No? Uploading. Okay, we'll see. Anyone getting error in lobe segmentation like this visualization? A very simple, well, you guys are in undergrad, we should not give homeworks, but what you can try to do is try to do the same thing in ITK Snap at home. You remember yesterday I was talking about another visualization tool, ITK Snap. You can try to do this, the same thing, upload the CT, upload the lobe segmentation and ITK Snap. So it's just like another visualization tool, nothing else. Like I think most of the tasks you can do using 3D slicer, but it's good to know other segmentation tool. Yes, it does, but like for basic level, it does not matter. Like I use these just for visualization tools, so they might have different set of interactive segmentation. So maybe 3D slicer, have some set of segmentation tool which are better for some set of radiologists, and then ITK Snap might have some other added functionalities which might be easy to use for some other set of radiologists, but we are neither of them. So we are just visualization guys, so just drag and upload and yeah. Oh, this L, P and S value, right? That's a good question. What do you think it is? What do you think it is? What's LPS in CT? Okay, okay. See, just scroll. So put your cursor here, and just scroll it. So what is changing and what is not changing? No, two values should change and one should remain stable. So you see, like L and A is changing, and here the X and Y is changing, and the Z is not changing. And then if you get your cursor here, the R and S is changing, P is stable, and here the X and Z is changing and Y is not changing. So it's basically which slice you are in. Yeah, exactly. Oh, so they uploaded the segmentation and then again the CT. So close it. Oh.
First I have opened lobe only, I mean CT only, volume only, and then mask I opened. This one I'm not sure.
No, that is definitely, yeah. Oh, they have not downloaded it properly. Just delete that and download the CT image once again. So it's just just downloaded up to some extent, and you might have stopped, or the internet might have stopped, or something happened. So delete the CT file. We'll wait for you. Can you redo it? Can you delete that, and we'll wait for you till then. Delete it, download it. Yes, just download it again. But delete the first one, otherwise, yeah. So for now, the segmentation is uploading correctly. Segmentation for, sorry? Oh, she is getting, okay. So they need help and she need help in downloading. Can you? Anyone here having problem? Yeah. What's that? I can you pass the mic?
Sorry, the lobe segmentation is not displaying properly, overlaying properly.
So how is it showing? Like I'll have to see it once.
Yeah, sure.
It's done, but you have to open it in 3D Slicer.
What happened?
I opened it. You just redo it.
Okay. Wait, this is a different CT. So you will have to upload the ct.nii.gz. So this is the ts_ct. Yes. Yeah. It's not working for you, right? No, this is the Python notebook. So I'll tell you what's happening here. So delete this. Can I? Yeah. So let me minimize this a bit. So you see this CT, this thing? Yeah. Drag and drop here. What's happening? Or the another way is add data. Choose files to add. Open. So you have to see this is volume. Wait, where did the other thing go?
Enter.
Yeah. Oh, enter?
Enter.
The CT. And then for the volume, where did you, oh this one, right? Same drag and drop, but change the volume to segmentation.
That was zip file I exported.
Oh. Oh, okay. Open. Segmentation. Okay. Can you close it and reopen once? Exit. No, this one is fine, just the 3D slicer. Open 3D slicer once again. You guys are able to get it? Sorry. Got it, right? Oh. So open it, I'll come back again. Yes, this is the wrong CT. So you'll have to, so this is the TS underscore CT. You'll have to upload the ct.nii.gz. So close it, or maybe it's fine, maybe. Okay, my eyesight is very bad. Okay. You don't have to increase it, like just drag and drop wherever the folder. Okay, I'll do it. I have not used Windows for such a long time, so. Wait, where is the, yeah, this one. Drag and drop. Okay, okay, okay. What happened? For recording. So there, and I think the person in the last bench also has. Like I was trying to help her. Can you also see what's? How about you guys? Were you? No. Solved, right? Solved. Okay. Okay. Okay, good that we did, because last day I was just like going as Rajdhani Express with 3D slicer. And now, so there is another live session. So even if there are a few other samples where we are missing it, we might be knowing how to visualize it again. So there are 2 live sessions today. By live session, I mean it's not like I will show what to do. I will show what to do and then you will do what I have already done. It's basically back calculation of the same calculation. Does it work for you, person in the last? Like, you got the lobe segmentation like this? Everyone got the lobe segmentation? Did you download the CT and everything? It's helping you. Anyone else? Can you check the last, like if she is able to get the lobe segmentation and everything? How about you? It worked for you, right? I was helping you. It's worked, yeah. This worked. So, like reiterating again, you'll have to upload the ct.nii.gz, not the ts underscore ct. Yeah, I think I should have kept that brats underscore 00000, that name. I just simplified it to ct and mr, and now that creates a problem. It's okay, right? So everybody is at this step should have the tumor, oh sorry, not the tumor, the lobe segmentation on top of the lung, right? Everyone is here, right? Right? Okay. Because the next step is also very crucial. So you should be at least here. Everyone is here, right? Okay. So now what you can do is you can scroll through and see the different lobes. See, it's segmented very accurately. Okay. So now the next part is how to visualize this lobes in 3D. So now it's all 2D, right? Like I can see different planes, but like, well, I want to see the segmentation in 3D, like rotating in the space. So to do that, click welcome to slicer, this thing. I'll repeat it multiple times. Click welcome to slicer, don't click anything else, I'll come back, just click welcome to slicer, right? And can you see segmentations here? Don't click, just like the movie, nahi dabana tha. Sorry? Yeah, I have not clicked. So just here, just to show everyone that you'll have to click the segmentations. Everyone is here, segmentations, now you can click it. So everybody should see this thing, segment 1, segment 2, segment 3, segment 4, segment 5. There are 5 lobes in a lung. If you are getting 4 or 6, that means your segmentation algorithm is wrong. Or sometimes maybe what happens is like you take the lung out, in that case you might have less different numbers, but for a normal lung you should have these lobes. Big tumor, take a significant part out, and small cell lung cancers are generally very big. So, okay, so everybody is here, this segmentation 1, 2, 3. So you remember yesterday I was talking about like how you can change the opacity and stuff. So click the display. Everybody can see this pane, right? No? Can see, right? You can play around with opacity. So what radiologists generally do is, so in order to see, well, if the segmentation is accurate or not, they change the accuracy and see the soft tissue, the difference between the soft tissue and air, and the soft tissue and bone, and the air and bone, whatever the structure depending on the anatomy, they try to see how accurate the segmentation is. If you want to check the, so basically for example, if I want to ask you segment the lung, you can still do a good job because the difference between the soft tissue or the bone around the lung and the lung space which is full of air, it's very simple to segment, right? So let's say you developed a lung segmentation algorithm and you want to check how accurate it is, you can just like play around with the opacity. And then space fill as well. If you want to fully fill the space, or if you want to just like have contours, so you see like this contours, and if you want to like just like copy this and plot it in a presentation, you can do that. Okay, we'll just wait for a few more guys to complete this lobe segmentation and everything, and then we'll move to the 3D visualization part. Yes. So contour is it's nothing. It's just like you will have to take this space fill. I don't know what this scroll thing is called, and just put it to 0, and you will get this contours. So this is good for visualization because like if you report this in a paper or a project report, you can still see the contours, and you will automatically know whatever is inside this contour is basically a label. So yeah. So like so now I removed segment 4 and 5. Like generally your natural eyes will not be able to say what are the two different lobes. But can you see this line here? Very, maybe in your computer it will be better visible than this one. So you can see a line. See exactly that is where the model is contour or model is segmenting it. So that is like for natural eyes or for naked eyes or for inexperienced eyes, lobe segmentation can be like, well, I don't see any difference, but like once you see the segmentation you can still figure out, yeah, there is some difference between these two lobes. So as of now I will just fill these, okay, and then if you click this show 3D, this button, and just click it, nothing is there, so but still click it. So what's happening is the segmentation is, so you just see a small window, the segmentation is somewhere in some axis. To bring it to the center stage, go to this small pin to the leftmost button. So you see this small pin, the small pin, and click this second center view icon. Okay, I'll just this. Click it. Now you can see the segmentation in the center view. I'll repeat it again. The small pin, the second icon. I hope it's the second icon for everyone, right? Yeah, okay, okay. Okay. Everyone's there? Second icon, click, can see the segmentation now? No? So like the segmentations are there, right, for you? And like what happens if you click the second icon? Oh, did you click show 3D by the way? आ गया? Okay. Okay. Everyone is still this step? Like can you see the slope segmentation? This is not it. So now like you see like this segmentation is not like this does not look like lung. So we'll have to change the view. So you see this 4 northwest east west kind of a thing. Click the A. Take your cursor to A, click A. Now you can see it looks like the lung that we generally see in images. I just scroll a bit. Right? Click the A. Just click the A line. Done? Everyone can see the lung in the non-natural lung format. And if you click the second like 2 icon, like this one basically, it will spin. Just for interactive visualization. Now, so that is it for today, like not for today, sorry, that is it for till I get the tea that is for me today. Stop the spin and then you can visualize this. Just one thing, if you have done this segmentation, you want to publish this or you put this on a report, how will you do that? Don't take screenshot. That is like don't take screenshot and put it in a report. You can take the picture but don't take a screenshot. So you see this eye option, click this eye option, remove the 3D cube, remove the axis and everything, just click this 2 icon and white background. So now we have the white background. Zoom till whatever level you want and then right click on it. So yes, repeating once again, click this eye icon, there is a white background, like change background whatever you want, like light blue or black or white. I just prefer white because all my one second. Okay. So everybody is till this stage. Click this eye, remove the 3D cube, remove the 3D axis label and have white background. Everybody is till this stage. Looks like normal human lung, right? Right click on it and just click copy image. And then if you open a presentation, here I'll do new slide, I'll just remove this and you can paste it here. So this is much better quality than a screenshot. Okay? So that's it for today till the break. Let me know if you have any questions during the break. Any questions? Any major questions? No, right? Okay.
Okay, so if you have no questions, we'll move ahead for a 10 minutes break and we'll reconvene in 10 minutes here. Move ahead for the break.
Okay, so we'll just reconvene after the break. I hope you had tea and everything. So the next thing that we'll try out, so I'll skip MedSam again for next day. MedSam, I don't know what MedSam has to, like the enmity with MedSam, I'm just postponing it. But I think total segmentator is something which you will find more interesting. So let's discuss that first, and then we will try to quickly do a same tutorial with total segmentator. Okay. So similarly, upload, I don't remember the file name. I think it's called NITR underscore session 2 underscore total segmentator. Right? Let me know if you have this file uploaded. Right? Everyone? So this upload the total segmentator file. The same procedure, file, upload, or right click and open in Google Colab. So I'll just repeat for the people who just joined. In the folder you will have a IPython notebook named NITR underscore session 2 underscore total segmentator. So just open that in Google Colab, similar like how you did in the previous few iterations. Okay, let me know if you guys are done uploading. Can you guys do that? How about you guys? Uploaded this? Right? How about you? You're able to upload this? Okay. So let me try to give a very quick background about total segmentator. I think just few minutes. So I have a habit of spending too much time on LinkedIn and and just like what papers are getting published, where my friends are getting their jobs and which jobs are open and everything. So I came across this post and I was like, so this is something, so this project was something that I thought of doing, like if there was enough data set, enough labels and enough training resource. And when I saw that this happened, rather than being sad, I was so overwhelmed. I just told Prateek that see, this is what we were talking about, and this is now there out in public, and he was like, no, that's not true. And then I had to show him a demo that, yes, see, this work, and they have a visualization or have a platform where you upload the CT image, and it will give you the segmentation. So what total segmentator does is it segments 108 anatomical organs right from the skull to the toe, all the bones, the gastrointestinal tract, different organs, the muscles, different muscles, and the cardiovascular system, which has the aorta and all the other vessels, arteries and everything. So basically everything that you want. So as bioinformaticians, right, or medical technologists, or whatever you guys like to call yourself, like it starts with, as I kept saying, it starts with segmentation. And whatever organs you might want to work with, which is solid organs, like of course blood segmentation, I'm pretty sure it's not like a thing, but any organ that you want to segment, total segmentator kind of like does that on CTs, and now I think since last year or last few months also on MRIs. So if you have a CT, a full body CT, or even like whatever part of the body you have, total segmentator can segment all the organs for you. And again, the code is very simple. Pip install total segmentator, and similar to lung mask, yeah, it just downloads a lot of things. And exclamation total segmentator dash I the path of the CT, and dash O the segmentation CT. So let's do this. Let me run it. I'll have to change the runtime type to GPU. Run it, and then again run it again here. So what should I do? Should I close everything? I know, but like how to close everything else and then put GPU here? Yeah, I think it worked. Sorry? I closed everything. So, oh, this one. No, this is the drive. I think it's closed. Yeah, I think it should work now. Let's see. So install. Oh. Where is that? Manage runtime, right? Manage sessions. Terminate other sessions. Yep, close everything that is there. Okay. I think I'll just refresh once again. But are you guys able to do it? Restart. So restart again. So don't do, so after restarting, right, don't run pip install total segmentator. Just start with the next step. Yeah, don't. So once you run pip3 or pip install total segmentator and it like restarted your runtime, don't run it again. Just run the next line, which is not working for me. Can anyone help me? Another account? Yeah, I think this will work now, hopefully. No. Okay. Do I have another account? So I'll have to give access to myself. And but let me try with manage sessions once again. Yeah, it says runtime disconnected. So it's still running, so I'll just stick with this.
After reconnect, you have to again upload the image file in the data section. Okay. After reconnect, you have to upload again the data, like the data file. You have to again upload it. Okay, and then you can do it. Yeah. That file name is ct.nil.zz. We have to upload it.
So are you guys able to run and did all the segmentations downloaded? No, right? No? Yes? It downloaded. It's done? Is it done for you guys, rest of you? Download like that the CT thing run for you guys? Everyone? Okay. Please wait for a minute, a few more minutes.
I think we can move ahead, okay? Like
Yeah. So like a note, like total segmentator, although it segments all the anatomical organs in your body, but let's say if you have a CT which is just capturing the thoracic region, or if you have a CT that is just capturing the abdominal region, you can still like use total segmentator to generate the segmentations only for those regions that you have. So we'll see how it works. Yep, it gave me an error. The input file does not exist because I never uploaded it. So meanwhile, just also upload the TSCT and the TSMR. So TS stands for total segmentator. So now we are going to use that, which some of you were visualizing it by mistake. So for the guys who have already for whom the segmentation is already done, just save that in your computer. So similar, like how to save, click that 3 dots, and then there will be a download thing. Just download it. It's not there. Oh, you can. I mean. So what you can do is you can zip it and upload. I'll share the code. 1 second. Or what you can do is try to take a look and see like if there are any segmentations like lung.nii or something like that. Download that first. Is there a lung.nii inside that folder? Everything is there, right? Just select like 3-4 segmentations, your choice, download them and try to visualize so everyone were able to run the total segmentator, at least the first 2 lines. Mm-hmm.
Then we have to download certain segments of it.
Yeah, just select the segmentations of your choice, lung or something like that. So meanwhile, open your 3D slicers again, like close it first so that the previous lung and previous segmentations are not there, and then open 3D slicer again. Are you able to reopen the 3D slicer? Now it works fine? I know. Yeah, for people like who have already done the CT, maybe it can also run the same thing for MRI. But for the MRI, do one thing, Don't use this MRI.zz, just use the TS underscore MRI. Okay, so I'm repeating once again. So the people like who are already done with the CT segmentations, leave it there. Just start running the same code. Just change the path from MRI to TS underscore MRI. MR, sorry, my bad, MR, and then run it. So for that you will have to upload the TS underscore MR. So I'll also do the same, and yep. So just a rain check, like everybody has the segmentation done, right? So you should be able to see the segmentations underscore CT in the left data pane or in the files pane. Everybody has segmentations underscore CT, right? Right? Okay. So do something like just try to download something. For example, I'm trying to I'm downloading aorta, and then okay, I'll just save it, aorta.nii, and then maybe the lung lower left. Yeah, I'll just try to like download these two labels. You can choose your own label. Just a note again, revisiting my note. So we are running this total segmentator on CT nii.gz. So if the organ is not there in the CT, it will still predict a mask, but it will be a 0 mask. So even if you drag and drop it here, there will be nothing. But let me see how accurately it predicted the aorta. So again, a quick reminder, you should not, like while dragging and dropping the aorta.ni.gz, it's a segmentation file, change from volume to segmentation, and then click OK. So I can see the aorta now in green. So aorta, like medicals, like people with medical background or anatomy background, what is the aorta? The microphone to someone.
It is the largest valve from where the blood flows enters the heart.
Okay. Okay. Like it's the main artery, the largest artery in the body. So that's what I was trying to say. Like the blood does not flow inside; it sends the blood to the entire body, to different part of the body. And it's a thick structure. I don't know if you have ever seen a real aorta or not. It's a very thick structure, and like with age you develop something called abdominal aortic aneurysms. So aneurysm is basically, it will just like the wall started to thin and it starts to bulge, and then calcium gets deposited, and if you are not if you are lucky enough, you will diagnose it early. If you are not lucky enough, like the aorta can rupture and it can lead to complications. And interestingly, many important people have died because of the rupture of aorta. Can you name any famous one? A very famous scientist died of abdominal aortic rupture. Albert Einstein. Okay, so this is the aorta. Any problem uploading the aorta? No, right? No. The aorta is not visible. Wait, the green. Oh, it's not visible here. Okay, let me. Or it's not visible for you. Here it's not visible, right? That is not a problem. We just learned how to do this display and everything. How about now? Still not visible? That is the problem with the lighting. You can see the green segmentation here, right? You can see, right? Okay. So let me try out with the another segmentation that I downloaded, which is the lung lower lobe left. again change it to segmentation, and yes, you see this is the lower lung lobe. So you can manually download these segmentations and keep uploading and see, if it's the right structure or not. So yeah, you may want to play around with it a bit. Any problem running total segmentator and downloading it and then visualizing in 3D slicer? You can do the same thing. You can get it to the middle. Oh, first I'll have to do so 3D, get it to the middle, run this, and then remove all the axis and everything, make the background white, and then start spinning the aorta. So this is the aorta, looks like it comes out from the heart and then goes all the way like towards the dorsal region, and then the abdominal aorta bifurcates into the iliac arteries. So while working with total segmentator, I learned a lot of anatomical terms. Okay, any problem? No, right? Okay, so you can try with MRs. We can try to visualize it later. Let us move on to the next topic, which is training your own NN unit. So till now, my bad. So till now we were all using already existing segmentation models, right? But now let's say you go back to your institutions and then you are working with a new data. So let's say you are working with, let's say, some segmentation which is not there in total segmentator, or you got your own data which has the lung CT and the tumor segmentation or whatever, depending on your task. You have the image and you have the segmentation. You want to train your own segmentation model because none of the existing segmentation model does that. So here is a very brief tutorial, like believe me, you don't have to do anything in this if you use this. Just you have to pre-process the data and you can train your own segmentation model. You can train your own NN unit. So NN unit was published in Nature Methods in 2020 if I am not wrong, and it became one of the state of the art method for segmentation. You can actually, like, it's a very good paper. You can read this paper maybe later, 2021, and it was published in Nature Methods. So it's basically NN means not a new unit. So it's unit but with a lot of hyperparameter optimization and automation. But like NN unit outperformed all the existing segmentation baselines, and it's pretty accurate for any task, I would say. So if you have an image and if you have a data set where you have the images and the segmentation files, you can use NN unit. And how to use it, I have compiled this code. It's very easy code, just change the path and everything and you can train your own segmentation. So first you'll have to install NN unit. And then as of now I have downloaded, I use this data, but I'll tell you how to structure the data. So you can also take a look at the NN unit GitHub. It's very informative, the NN unit GitHub page. Here they have very good documentation about how the dataset structure should look like, etc., how NN unit works. If you have a 2D dataset, for example, if you want to segment the lungs from chest X-ray, you can use NN unit. If you want to use this to train a CT, like segmentation for CT, you can do that. So it's like very like generalized in that manner. Now, sorry. for usage, wait, sorry. Yeah, so it supports PNG, TIFF, NII, NRRD, all the different imaging formats that you can have. So how you should keep your data? For example, like you should have NN unit raw folder. Mind you, the U and N should be capital. You can't mess up with this capital and small. So you should have a folder like NN unit raw, and in that you should have different data sets that you want to train in this format. Dataset underscore something 3-digit number from 001 to 999 underscore any name that you want to put. So this is not standardized. This is your name that you want to put, but this one should be same. So for example, you see like the data set is same for everything, it's just the number changes, and this number should be unique. Like for example, today you are trying an experimentation data set 001 underscore, let's say tumor segmentation. Tomorrow you are trying to redo another experimentation, don't put data set 001, just put it something else, 711 or 911, something like that. So inside this data set 3-digit number underscore something, this is how you should keep your data set. Images TR, that means images for training. Labels TR, that is labels for training. So in the images TR you will have your the image files, and inside labels TR you will have your segmentation files, and a dataset.json, and images TS is optional. That's all. And mind, like this T should be capital in TR, and this T should be again capital in labels. And inside this, you see, you should have all the imaging files, and inside labels you should have all the label files. Okay, so let's see, restart session. I will run this, I will download this data set. So after you have formatted this data set in this format, what you should do is you should just run this command, and this 106 is basically your dataset number, which is this one. That's it. So if you can keep the dataset in this file folder structure without messing up with the capital and small letters and the underscore and the number and everything, you just have to run this line. And this 106, this 106 changes to whatever the dataset number you keep, 711, 911, like it's totally depends on you what you want to put, and then run it. So what this will do is this will automatically pre-process the data. So you remember yesterday we were talking about normalization, bringing the pixel value up to some range, this like multiple things, you don't have to do that anymore. NN unit automates everything. So NN unit is, I would say, particularly built for clinicians who want to use segmentations but don't want to write code. I mean, they don't have the time or bandwidth or the interest of writing this dense normalization and pre-processing codes. So it's very useful for them. Just keep the images and the labels in that particular file format, run this command, have a good GPU, start your segmentation training, and it's very accurate. And after that is done, this is your training command, just one line. NN unit underscore train 2D, NN unit trainer v2 task 106 multilung 0. This 0 means 0 fold. So if you want to train it for 5 folds, just so that is basically this data set that I downloaded. I can show you. So here the data set that I downloaded already named it as 106. You can name it anything for your data set. So for example, I was initially trying to do this with Brat's dataset, and so this is what I was trying to download, but it was so large, and the internet was was a bit slower. So this is how I kept my Brat's 2D dataset. Can you see this folder? Dataset 143 Brat's 2D, and inside this I have a dataset just .json and the images tr file and the labels tr file. Inside the images tr I have all this brain MRI scans. Inside this label I have multiple labels. So it's black because it's 0 to 1, you can't see it with naked eye, but the labels are there. And then this is the dataset.json, where you just say that I have this different MR sequences, flare, T1, T1 post contrast, and T2. Two things I want to segment: background, which is anything that is black, and the tumor, which is anything that is white. And this is the number of training samples, 776, and the file ends with .png. So this is how your dataset .json should be, and then you are good to train. So I have a question: why labels tr has 776 items and image trs has almost 3000 items? Sorry? No, it's not augmentation. So you see, like for tumor segmentation, I was discussing yesterday that you need 4 different sequences of MRs: the flare, T1, T1 post contrast, and T2. So how NN unit basically trains itself is, it takes all the 4 sequence, feed it to the unit structure that it has, and provides one mask output. So for example, if we have this label, let me view as list. So if you have this patient, Brat's 2021 _ 00016 PNG, for that we will have 4 Brat's 2021 _ 00016 files. So what are these 4? The 000 is, if I go to the dataset.json, is my flare. The 001 is my T1, the 002 is my T1 post contrast, and 003 is my T2. So if you have multiple sequences for the same patients, you name it like this: _ 0000, 0001, 0002, and 0003. So for each label there are 4 MR sequences. So coming back, after this pre-processing is done, yeah, I hope this pre-processing is done. I will just hide this 5 different folds and I will start running the training. Yep, it says I am running an NN unit 2D, there is only CT, batch size of 104, and creating a new 5-fold cross validation, training fold 0, there are 50 in training, 13 in validation. LR learning rate is 0.01. It just give me a warning that you are trying to train on CPU, doesn't matter. I am not going to train it till end, but yeah, you should use GPU. I'm just trying to wait for one epoch, but this is how you can just train your own NN unit if you have the correct file folder structure. So segmentation is very easy. Any questions? So what I would suggest is, I will share, like after the session, of course it takes time, after the session I will share a Brat's, that 2D folder that I am trying to download with you. You can, I have not done anything, you can try to run your own NN unit code for the Brat's tumor segmentation, like after the session is done. Yes. Microphone.
Sir, learning rate is 0.01 you given. If it is, I'm increased to LE4, like 0.001. So what are the consequences we can face that one? Are you observe anything regarding to this one?
So okay, so I can answer this question in 2 phases. First, I don't decide the NN unit 0.01. So this phase, you see like this NN unit plan and pre-process does not only pre-process the data set, it also plans the training. So based on the data set, it starts with 0.01, but after every iteration it can change the learning rate. So now it's, let's say, 0.01, next it can, like in the next iteration it can go to 0.001. But so NN unit is very much automated, that's what I was saying, you don't have to do anything, you don't have to train multiple times. But again, second phase of my answer is, I have seen that if you have a very small data set and if you want to train that data set, like with of course you want to have good accuracy, but the data set size is small, and to get better accuracy you want to train a bigger model. So model is big and the data set is small, so you would like to train the model very slowly. By slowly I mean the learning rate should be decreased. So so rather than keeping 0.001 or 0.0001, you can keep it like up to 5 decimal points, 0.00001 or 0.000001, something like that. But you should not train. So for example, if you are planning to train your model for 500 epochs, you should not keep the same learning rate. What you should do is you should put a decay. That means, let's say if you started with 0.01, let's say even for smaller data sets you would like to start with like higher learning rate, so that the first few iterations the model learns faster and then you slow down. So for example, for the first 50 epochs you train with 0.01, next 50 epochs you train with 0.0001, and then the next 200 epochs you train with a very lower learning rate. And so that is called weight decay. You should also have something called the scheduler. So that will check. So scheduler is basically, I mean, it goes into again model optimization stuff. So let's say if you have a convex function and if the goal is to reach the global minima, and if you have the step size which is very big, that means the model will never reach the local minima. So you should like slowly gradually reduce the size. So if you are on the top of the hill, you would likely to come down fast initially because you are not even near to the global minima. So have large steps, and then the more you reach the the global minima, reduce the learning steps, because if you don't reduce the learning steps, even if you are here, you will still go here and there because the step size is very large. So learning rate, scheduler, and then also what you can have is early stopping. If your model is not training anymore, just stop after 20 epochs if the loss is not converging. But again, coming back to that, there is no how to say correct answer how to train a deep learning model. You should have all these recipes, but again that does not guarantee that if your training is very difficult you will get the best accuracy. It's all about training, they have a good model, big data set, everything. Okay, let's see if we are there for one epoch. No, I mean of course we are training on a CPU, so it will take time, but yeah, if I know, and running an NN unit in Colab is difficult, but you can take this code if you have a good GPU in your lab, or if somebody is nice enough to give you GPUs for training. You can come and contact Samyajit. So yeah, so that is basically the summary of this lecture. We will do till 5:30, so I have 12 more minutes. Please bear with me. I know it's Sunday, but I have just one topic left. Very small topic. You don't have to do anything, you have to just listen. Yes. Yeah, any question? Sorry. The NN unit, I will send everything in the last because I have to compile, sit down and compile. And to be very honest, I am not getting any time between. Sorry? There are many actually in the GitHub, but that one you opened, I didn't find that. Oh, just type NN unit. Just type NN unit, don't mess up with the spelling, and the first thing you will get is NN. Okay. So why I want to emphasize, because this is the last and I would say one of the most important thing if you are trying to do some project. Yesterday I discussed radiomics, and if you listen to the lectures of Dr. Prasanna, he was emphasizing on this radiomic features and then doing all the different downstream tasks using radiomic features. But now if I tell you, and also I discussed TCIA, you have those huge data sets, and I think you had a question that how can I download this data set. Well, pathology data set I can't help, but at least if you are trying to work with radiology, I have a good solution for you. So these data sets are huge, like if you try to download these data sets, it will be in GBs, and then processing it will need time, and it will you will get multiple errors, and at some point you will just dump it. But recently there is a link which is called Radiomics Hub. What they did is very nice of them. They took all the data sets that you need, LIDC, IDRI, non-small cell radiogenomics, non-small cell radiomics, UCSF, UPenn, etc., and downloaded those data sets, pre-processed them, and provided you the pyradiomic features. So you don't have to do anything, just select what research you want to do. You want to do work on lung cancer, take these two data sets. You want to work on prostate cancer, take this data set. You want to work on head and neck squamous cell carcinoma, take this data set. You want to work on kidney, take this data set. You want to work on liver cancer, HCC TACE, take this data set. So you don't have to download this data set anymore. Click here, you get all the radiomic features extracted. And not only the radiomic features, also their labels. So for example, this patient, HCC001, is it dead or alive? Dead. What's the overall survival? This one. Did they have hepatitis? HCV only. What was the age? 71. What was the gender? Sex? 1. Smoking? 1 means yes. Alcohol? 1 means yes. So you get all the patient history and their radiomic features. So the pyradiomics tutorial that I gave you yesterday, you don't need that anymore. But still, if you get your own data, you still need to run the pyradiomics, and I hope it was very easy, just few lines. But if you want to work on some public data sets, just save your time, take the radiomic features from here and run your classification model. But now how to run your classification model? Yes, sorry, any question? No? Okay. So I downloaded the non-small cell lung cancer radiomics, that is basically this data set, and here of course there are all the radiomic features like shape, texture, GLCM, and all those things that I discussed yesterday. So I downloaded that, and I have all the pathology information like what's the age, what's the clinical stage of the tumor, and the histology. That is what I'm talking about. So if you see the histology, there is large cell, there is squamous cell carcinoma, and there is adenocarcinoma. Now let's say from this set of patients we want to see if these radiomic features are predictive of classifying squamous cell carcinoma and adenocarcinoma, that is LUAD versus LUSC. So this is a very simple code, but let me first discuss the pipeline. Let me ask you a question. So there are almost like, I don't know, like maybe more than 100 features here. Do you think all of these are important? No. I think Dr. Prasanna also discussed that. Not all the features are important. So how would you know which features are important? So you have to do something called feature selection based on ranking. So the feature selection can be done like using various techniques, but like ranking them is one of the, using ANOVA, which is a statistical method, is one of the best approach to do. So here I just download them, load it here. Let me load it again.
Excuse me.
Yes.
When you say ANOVA,
yeah,
what form of ANOVA? Any form, 2 point, 3 point, anything does the same work?
I don't think anything does the same work. I think what I take is the most recent one, which is ANOVA V2.
Okay.
Or ANOVA V3. I have not used V3.
Okay.
Mostly we use, it's not about me using, I use this fclassif, this sklearn library, and then here I have this fclassif function which uses ANOVA. So I think if I am not wrong, they uses
inbuilt class. Okay.
Inbuilt.
Okay,
Yes.
I get it.
Yes. Any more questions? No. Okay. So let me try to upload. I have downloaded that in my local system. So let me Okay. So my features and labels both are uploaded. So let me run it one by one. So here what I do is, so if you see this radiomic files, there are some like columns which are not radiomic features, but it has some information. For example, the ROI, the image path, the segmentation path, and the extraction ID. I don't need these things. So what I'm doing is I'm just like dropping those columns, dropping those, and from the label you can do multiple things. You can do survival classification, blah blah blah. But here we are doing subtype classification, squamous cell carcinoma versus adenocarcinoma. So I'm only interested in this histology column. So what I do is I first calculate how many patients are there for which. So for squamous cell carcinoma we have 152 patients, for large cell we have 114, for adenocarcinoma is 51. So I just remove the large cell and NOS, and I'm just taking this 152 and 51 patients. So yes, I do it here, and then my target class is adenocarcinoma and squamous cell carcinoma only. So that becomes this 202 patients, and then I map the class. So adenocarcinoma is labeled 0 for me, and squamous cell carcinoma is labeled 1 for me. Then I drop the unwanted columns. Now here I built a pipeline. So as I said, the first thing is you have to standardize the data or normalize the data. For that I use an inbuilt function called standard scalar. Then what I think Salik was asking, select the best k using ANOVA. Which version of ANOVA? So this is what the select best feature is happening here. And then finally is the classifier. So normalizing, selecting best feature, and then classification. This is the pipeline. So my random forest is one of the the best classifiers that you can use. You can also use support vector machines or decision trees. You don't have to write code for anything, they are already there in sklearn. So you can just pick and play with these classifiers. But what I would suggest is, don't spend too much time like experimenting which classifier is working the best. For that we have another library called Optuna, which does this hyperparameter tuning or hyperparameter optimization. So what is hyperparameter optimization? So you want the best model and you don't know what your best model can be, but you have a fair idea that it will be somewhere between, or it can be somewhere any model among support vector machine, logistic regression, decision tree, or random forest. So you want to feed this to the hyperparameter optimization framework and let it pick which one will work best for you. And if the model selects SVM, it does not know what the sigma function, the gamma parameter and the C parameter will be. So all these things are done by hyperparameter optimization function, that is Optuna. So you don't have to worry about, so it will finally, the final output will be the best model you can have. So I am downloading Optuna, and then I am running this hyperparameter optimization for only 20 trials. So here, rather than keeping 20, you can do like 500. So like the more the number, the better search it will do, the best parameters. So as of now, just for time constraints, I am doing 20. I am already at 13. So you see what's happening here. In trial 0, the value my AUC is 52%, which is not good. I don't like it. And the best features were 24 top features were selected. We used a random forest model with so and so parameters, but I don't like 52 AUC. I want more. So the next iteration, trial 1, what happened is it changed from random forest to SVM. The Optuna is doing it in itself. I am not doing anything. And I increased the number of parameters from number of best features from 24 to 48, and it came 54. I don't like that anyway. So you keep increasing, and somewhere you have so this is the best configuration with best parameter, the top parameters 90. Logistic regression was chosen the best model, and this is the log reg C value. and yep, you see my test accuracy is 60%. So I started with 50, 52, and now it's 60, and AUC is 52. And then you can see like adenocarcinoma, the precision is 33, squamous cell carcinoma, the precision is 83. Why the model is predicting squamous cell carcinoma better? Any idea? It had more number of patients. So it's a very imbalanced data, and that is why the model is overfitting on squamous cell carcinoma, which is not a good thing. But there are other ways to deal with class imbalance that we'll discuss later. But yeah, and these are the top, I'm sorry. Okay, I'll check this error later, but anyway, summarizing, you have radiomics hub from where you can get all these features. You don't have to download the image, you don't even have to see the image anymore. You have all these radiomic features, and you can use this entire pipeline end to end to do a classification. And also you don't have to burden yourself with selecting the best model, trying to improve the accuracy. This hyperparameter optimization library is going to do that for you. So at the end you will have the best set of results that you can have. Okay, any questions? Okay, if no, then we'll conclude. Thank you.
Any questions? No?
Please try this out on your own, and I'm here till 30th. If you have any doubt, let me know.
Yeah.
Even after the session timings, that's also fine.
So a lot of effort has gone behind preparing these codes. Okay, so please take this opportunity to learn, and I hope upgrade your skills as well. You have come also from far places, so it's time to actually, in addition to enjoying the nice winter weather, please do please do take take benefit of these things. Anyway, so I think with this we finish our experimental session. Thanks to Moinak for all the explanation and support, and I hope you all had a good session today. Yeah, a round of applause to all of you will be good. Thank you very much. We will resume tomorrow at 10 a.m. Tomorrow we have 4 lectures, so we have almost halfway through the course. 2 more days remaining. So thank you all very much. So please reach the auditorium again by 9:30 tomorrow, so we can start on time. Thank you.